joy that we welcome you to the inaugural session of GIAN course, Global Initiative of Academic Network, hosted here at National Institute of Pharmaceutical Education and Research, Mohali.
Today marks the beginning of a transformative journey into the molecular mysteries of fluorination, a topic that has revolutionized drug discovery and therapeutic design. With over 40% of recent FDA-approved small molecules bearing fluorine atoms, this course couldn't be more timely or impactful.
To commence this prestigious event, may we request our esteemed dignitaries to grace the dais. Professor Rand Altman, Chair in Pharmacy, Purdue University, who is our guest of honor and course instructor.
Professor Inderpal Singh, Head, Department of Natural Products and Associate Dean, Alumni and International Affairs.
Professor Gangaram Chaudhary, Chief Guest and Head, Department of Chemistry, Punjab University.
Professor Gurjasprit Singh, Local Coordinator of GIAN, Punjab University.
And Dr. Deepak Salunkhe, Course Coordinator, NIPA Mohali.
Let us now invoke the spirit of knowledge and enlightenment through the ceremonial lighting of the lamp. This flame symbolizes the illumination of intellect, the warmth of collaboration, and the brilliance of scientific inquiry.
We request our dignitaries to kindly proceed for a lamp lighting ceremony. As a token of our deep appreciation and respect, we now proceed to felicitate our distinguished guests and speakers who have traveled across borders and disciplines to share their wisdom.
Now may we call Professor Inderpal Singh to present a floral welcome to our guest of honor, Professor Ryan Altman. Sir, please. Thank you, sir.
We'd now like to request Professor Inderpal Singh to graciously greet Professor Gangaram Chaudhary, the chief guest for today's event.
We'd now like to call upon Professor Inderpal Singh to cordially welcome Dr. Madhuri Patil, coordinator of GIAN course.
Yeah, ma'am.
Thank you, sir.
We would like to request Professor Gurjaspreet Singh, local coordinator, to present a token of appreciation to Professor Inderpal Singh.
Thank you, sir. May we now request Dr. Deepak Sarunke to felicitate local coordinator of GIAN, Professor Gurjaspreet Singh. Sir, please. Thank you, sir.
We now like to invite Professor Gurjaspreet Singh to share the information about the GIAN initiative of human resource development and the role of Punjab University in arranging this course.
A very good morning to our distinguished speaker, Professor GIAN, Chair in Pharmacy, Purdue University, Professor Inderpal Singh, Head, Department of Natural Products and Associate Dean, Alumni and International Affairs, Dr. Gangaram Chaudhary, Chairperson, Department of Chemistry, Punjab University, Chandigarh, Course Coordinators, Dr. Deepak and Dr. Madhuri, Dr. Deepak from Department of Medicinal Chemistry, Naipur, and Dr. Madhuri from MCMDAB College, Chandigarh, faculty members, all participants, and everyone present here. I extend a heartfelt welcome to all of you to the international workshop on understanding the mystery of fluorination in medicinal chemistry, organized under the global initiative of Academic Network GIAN. Professor GIAN's pioneering research work lies at the interface of synthetic, organic, and medicinal chemistry, focusing on organometallic and organofluorine transformation and the design of fluorinated structure with unique reactivities. His collaborative work addressing pain, anxiety, mood disorders, and aging continue to make significant contribution to both chemistry and medicine. We are truly honored to have you with us today, Professor GIAN, and we look forward to gaining valuable insights from your expertise. The global initiative of Academic Network GIAN in higher education was launched in 2015. It is a flagship program of the Ministry of Education, Government of India, designed to tap into the global talent pool of scientists, innovators, and entrepreneurs, and to foster their engagement with the Indian institution of higher education. GIAN aimed to catalyze excellency in higher education institutions across the country, including all IITs, IIMs, Center Universities, IISc Bangalore, IISers, NITs, IIITs, progressively extending to reputed state universities. It is a dynamic program that promotes participation of international faculty as a visiting professor or professor of practice, offering specialized 5 or 10-day courses to enhance academic collaboration and knowledge exchange. The first GIAN course at Punjab University was conducted in 2016. Till date, 29 courses have been successfully organized, and we look forward to conducting many more in the future. Punjab University has submitted 40 new proposals under Phase 5 for upcoming financial year. Under phase 4, one course remain pending and it is scheduled to be connected before December 25. I wish you all an enriching and insightful learning experience with Professor GIAN. Thank you.
Thank you, sir.
To introduce the essence and structure of the present GIAN course, I now invite Dr. Deepak Sarunke, our course coordinator, to briefly elaborate about the course. Sir, please.
Thank you, girls. So I think welcome all of you, and I really feel very happy. About 2 years back, I along with Madhuri, we wrote this like a joint course. Most of the efforts are with Professor Altman, who actually is an expert in the organofluorine compounds, and we thought that this is something very interesting area. We should at least. Maybe we can say that we are course coordinators, but more like maybe we will be sitting all the time in the course, and we would like to learn many aspects of fluorine chemistry as you will be learning. So so the overall course is a 5-day course. Already the lecture schedule is shared with all of you. Apart from whatever we planned, I am very happy that Professor Bhartam, Dr. Ravi, Professor Banerjee, Professor Chatterjee from IIT Roped, Professor Ramashastri from ISR Mori, we added like 3-4 more lectures, which will definitely add an extra edge to whatever we planned earlier. So with this, I'm really looking forward to have a very interactive 5 days. Thank you.
Thank you, sir.
Moving ahead, we now request Professor Inderpal Singh to address the gathering and say a few words. Sir, please.
So, very good morning to all of you. So, respected Professor Gangaram Chaudhary, Chief Guest for the day, Professor Altman, Guest of Honor, Professor Gurjasprit Singh, Local Coordinator of GIAN, and Dr. Deepak Salunke, Course Coordinator, and Dr. Madhuri, Course Coordinator, my faculty colleagues, and dear participants. A very warm welcome to all of you. To Naipar Mohali for understanding the fluorination in medicinal chemistry. So, for those who are coming from outside, NIPER is an institute of national importance established by the Government of India under the Act of Parliament with an objective of becoming a center of excellence in pharmaceutical sciences, teaching and research. So NIPER Mohali offers 16 courses in master's program in 11 different departments, and currently more than 450 master students are enrolled at NIPER and more than 200 PhD students are enrolled at NIPER. NIPER has been ranked consistently highly in NIRF ranking as well as QS World University rankings. At NIPER, we have several national level centers, including one of the recently established Center of Excellence for drug discovery in antiviral and antibacterial areas. So, as for this program, as already said, fluorine is a very important molecule. As already said, 30 to 40% of FDA approved drugs contain fluorine. And there have been so many books published on fluorine chemistry that itself indicates the importance of this topic. GIAN, the global initiative, has already been introduced by the coordinator, Dr. Gurjasprit Singh, and I will not dwell much into that. And today we have The faculty for this course is Professor Ryan Altman. Three eminent faculty will be conducting this course. Professor Ryan Altman will be teaching you over the next 5 days. He has PhD in organic chemistry from MIT with Professor Buchwald. And after completing PhD, he has been in University of California at Irvine, and then joined University of Kansas, and currently he is at Purdue University in the Department of Medicinal Chemistry. He has worked extensively on fluorine chemistry and will be guiding you about the fluorine chemistry. The other coordinator, second coordinator, is Professor Deepak Salunke, who received his PhD from NCL Pune, has been a postdoc at Kansas University, has got a Indo-French sandwich thesis scholarship program, has worked in industry at Venus Therapeutics and Sai Life Sciences, and then at Punjab University, and currently he is our colleague at Department of Medicinal Chemistry at Naipur Mohalli. The third coordinator for this course is Dr. Madhuri Patel, who has completed her education from Savitribai Phule University and has worked at CSIR NCL Pune. She has been a postdoc at University of Kansas before joining MCM DAV College at Chandigarh. She has received DST Women Scientist Fellowship. And this course has been possible with full support from our director, Professor Dulal Panda, as well as Vice Chancellor of Punjab University, Professor Renu Veg. And I am very thankful to both Professor Panda and Dr. Renu Veg, as well as Dr. Gurjasprit Singh, who is local coordinator, for bringing this program to Naipur Mohalli. And I hope that in these 5 days you all have a very fruitful deliberations on fluorine chemistry. Welcome to Naipur and enjoy your learning and stay at Naipur Mohalli. Thank you very much.
Thank you so much, sir.
May we now request Dr. Deepak Salunke to introduce Chief Guest Professor Gangaram Chaudhary. Sir, please.
Again, I am so happy that I am getting this chance to introduce a very eminent personality, also a very good teacher, and truly a very good friend also. So because I feel really lucky that I got chance to work with Professor Gangaram Chaudhary as well as Professor Gurjasprit sir at Punjab University for 10 years, and it was really a lot of learning experience working with them. I wish sir was a chairman 2 years back. This would have not been the situation. Okay, so Professor Gangaram Chaudhary is a professor of physical chemistry and chairman in the Department of Chemistry, Punjab University at present. He is also a coordinator of RUSA and he's the president of the institution's Innovation Council and coordinator of the DST Stuti program at Punjab University. Professor Chaudhary is actively engaged in the synthesis of nanomaterials via green methods. He has published over 240 research articles in high impact journals and he has secured over 5 crores of funds from the extramural funding. I would like to highlight here that majority of the funding for the university professor they bring by their own extramural from extramural grants. He has been instrumental in providing valuable contribution to industries in Punjab and Himachal Pradesh, and he has got a consultancy funds of over 1.35 crores so far. As a successful director, Safe CIL, I have seen his work at Safe CIL. He was instrumental in bringing over 21 crores from DST and other funding agencies to really build this state-of-the-art facility, and which is helping over 6,000 students all over India. Recognizing his outstanding contributions, Dr. Chaudhary has received prestigious awards. A few I'm mentioning, including the Indo-US 21st Century Knowledge Initiative Best Researcher Award, a couple of times at least from Srimati Premlata and Dr. D.V.S. Jain Research Foundation Awards, and many, and also every year maybe he's getting Best Publication Award from this foundation. Professor Chaudhary, the CV is very long because of the time. I just wanted to highlight one more thing. Dr. Chaudhary is an editor of BMEF Science Partner Journal, Associate Editor of Frontiers in Nanotechnology. He has guided over 60 master students and already given PhD to 23 PhDs so far. With this introduction, I kindly request Professor Gangaram Chaudhary to say a few words.
Thank you, Dr. Deepak, for your kind words. Distinguished speaker of this GIAN program, Professor GIAN Altman, Professor Inderpal Singh, old associate, my old associate, Dr. Gurjaspreet, local coordinator of GIAN, Dr. Deepak and Dr. Madhuri, course coordinators, Professor Bhartam, Professor Ravi, other faculty members, and dear participant. A very good morning to all of you. At the outset, I am highly thankful to Professor Gurjaspreet and Dr. Deepak for giving me this opportunity to visit here and to be with you in this session. As all of you are aware, that is why you are here, that carbon-fluorine bonding offer unique properties, particularly chemical stability and thermal stability, extremely high thermal stability, and they are being utilized not only in medicinal and therapeutic applications, but if you look at electronics, coating, because of their stability, so they are very, very important compounds, particularly polymers of fluorine like PFAS. So I am not involved in synthesis and exploring application of carbon fluorine bonded compounds, but I have been associated with these polymers of fluorine in a different capacities, because chemical and thermal stability of these compounds are very, very high. So they are very, very difficult to degrade. So since I have been associated with the effluent treatment of various industries, so there is a strong urge to remove or to eliminate these kind of contaminations from wastewater. Even particularly in Baddi region, there are a lot of pharmaceutical industries. Those are using PFAS and other compounds. So we have been working there. My two students, they are particularly working on elimination of PFAS from industrial effluent. So I found this topic very, very interesting, because in coming 5 days you will come to know that how important properties these compounds offer. So I believe that these 5 days will be very, very fruitful and will be have a great learning experience for all the participants. Thank you so much.
Thank you, sir, for enlightening us with your words.
May we now request our guest of honor and course instructor, Professor Rand Altman, to share his thoughts. So please.
So, good morning, students, colleagues, friends. I appreciate all the welcome and kind words already expressed, so thank you all. I have a long history of engaging with Indian researchers, going back to my graduate education, when they were peers and colleagues training with me. Since being a professor, I've trained 13 Indian, mostly postdocs, but also undergraduate students. And so I've had a Serb visiting fellow work with me, and that Serb program allowed me to come back a couple of years ago, in which I actually visited Nipur for one evening. And thank you very much for the hospitality back then. I think that was 2022. So I have a long history of engaging students. I'm happy to continue now through the GIAN course, the GIAN network of courses. I'm happy to talk about this topic. It's a passion of a topic. It initially started when I was a student, a graduate student. I was intrigued about the physicochemical perturbations imparted by fluorine and the impact that fluorinated compounds can have on biological systems. And what started as an inquiry, what started as just a question, I wonder why, ultimately became a career. So that inquiry started in 2006, and it continues today, and that's what we'll be discussing. So hopefully the passion becomes apparent in addition to the science. When I teach from a very physical standpoint. I think in education, as you're learning about your field, your desired field, it's important to step back at the field more basic, more fundamental. If you want to be an excellent astronomer, you need to know physics. If you need to be a great physicist, you need to know your calculus. If you're going to be a great medicinal chemist, you need to be a chemist. And if you want to be a great chemist, you need to be a physical chemist. The physics and understanding the physical organic chemistry is going to be more impactful for understanding the why fluorine perturbs properties, and then you can apply the why in many different settings as you move forward throughout your career. So as much as possible, I will encourage people to think back about the physical properties of molecules, and then we will move forward into how those molecules behave in biological systems. Okay? So just prepare your mind for that. I'm happy to share this passion, this line of inquiry with you. I look forward to the week ahead of us. I hope it'll be interactive. I hope you're not too quiet and mute and just kind of sit there and take it in. I hope that you'll stop and pause and interact and engage, ask questions where you have questions, and we'll have a positive week. So thank you very much. I look forward to a great event.
Thank you, sir, for sharing the insights. As we embark this 5-day academic odyssey, we'll explore how fluorine, nature's most electronegative element, can modulate molecular conformation, enhance metabolic stability, and fine-tune pharmacokinetics. From selective CF bond activation to fluorine-19 NMR spectroscopy, this course promises to bridge synthetic chemistry with therapeutic innovations.
With hearts full of anticipation and minds ready to absorb, let us now take a short tea break. Please join us outside the seminar hall for refreshments and informal interactions.
We reconvene at 10 a.m. sharp for the first lecture by Professor Altman on physical principles, stability, and reactivity patterns of fluorine and fluorinated groups.
so I leave this one turned off. So I guess we have a few minutes just to chat. Maybe I need these so I can see you better, right? There we go. Okay. Is this on now? That's on now. Okay, so we should get into course material. Before we get started, I did want to learn a little bit about you all. So I want to adjust my language, my discussion as we go through. I think Dr. Deepak already started answering some of these questions, but just hands up right now. Are you a bachelor's student? Bachelor's level students? Master's level students? In the back. Why do master's students always sit in the back? Okay. Doctoral students? Okay. And you guys are on the side too. Any postdocs? And clustered together in the, you guys always sit, postdocs always sit together? Okay, osmosis. It's supposed to work where you like distribute across, not separate. That's an entropy going the wrong way. Okay. And then, okay, go ahead, raise your hands. Okay. Oh, so nice to see you all. So welcome everybody. I will try to adjust the discussion. It does help to know that right now we don't have any bachelor's students, so I can start from a little bit more of an advanced position. And anybody else that I didn't? Okay. So, maybe that first question right there. True? I know that fluorine's important. Okay. I don't know that fluorine's important. Do I need to convince anybody here? You heard in the introductions about 40% of recent approvals are fluorinated. Historically, about 30% of molecules are fluorinated molecules. And why? And the why is what we're going to talk about over the next several days. Who knows about all the different types of fluorinated functional groups that are out there? You've seen an aryl F bond. You've seen an aryl CF3 bond. What are some of the other substructures you're aware of? But the types of substructures themselves, how many do you know beyond CF3 and F? The group, what other types of groups do you know of? Single atom substitution, yeah. So I hope that we can learn some diverse structures and understand where they're relevant and why they might be useful. So that should be a goal. That should be something you keep in mind where we're going as we move forward. So the last one there, who understands the why? So why does fluorine and fluorination impact all the properties that make it useful for drug discovery? Who understands why? So it's a smaller size, absolutely. Why does that matter? Is it? It's a bioisosphere of hydrogen. What else? So CF3 would be a bioisosphere of CH3. So there are many myths in fluorine chemistry, and we want to avoid using myths to guide our rational design. And so as we go through, we're going to talk about some myths, some lore. We'll explain why those myths and those lores are true as we move forward, but we're also going to dispel myths where they're not true, and we'll come back to some of these things. But there are many whys, and I want to ensure that everybody leaves here understanding the basis for why fluorination works. It's important for several reasons. If you understand the why, you might be able to extrapolate the knowledge and take it to other systems. So if you are dealing with fluorine, you say it's an electron withdrawing group. Okay, what other electron withdrawing groups might modulate a molecule? So you might be able to extrapolate the basic principles outside of fluorine chemistry. So that's one thing to keep in mind. Okay, the second thing is you have to understand why, so you're not just randomly making a bunch of compounds that may or may not solve the problem you're trying to deal with. You only have so much time. You only have 2 hands. You can only run 5 or 6 columns at a time, right? I think I heard that from some students a couple of days ago. Being able to rationally design compounds can save you time in the long run. You can design fewer compounds, address the issues with your molecules more directly if you understand the why. And so that's what we want to do. In order to understand that why, we need to understand the physical chemical properties that are perturbed by fluorine. So as medicinal chemists, as discovery chemists, we're definitely interested in understanding how fluorine perturbs all these physicochemical properties. And when you think about drug discovery, drug design, you're always measuring and checking and testing on all these types of properties. I'm going to use the term DMPK. A related term is ADME, administration, distribution, metabolism, excretion. Everybody's aware of that. And DMPK is related, distribution, metabolism, pharmacokinetics. So if I'm using that terminology, I've let you know, but if you don't remember it, let me know, and I'll remind you all, okay? So as medicinal chemists, we're using DMPK considerations to select molecules, to promote molecules, and fluorine is going to perturb many of those properties. That's why it's so valuable. But unless you understand the basic physical chemical properties that are being modulated, it's going to be difficult to rationally use these strategies. So again, the goal today in this exact lecture and the tutorial that follows it up will be to focus on really basic principles. So for a little bit, you're going to feel like you're in like an undergraduate or undergraduate course on basic chemistry. And we're really going to focus on fluorine. And then we're going to move forward, start talking about organic fluorine compounds and some of the reactive intermediates that form, and then we'll eventually move into the drug discovery. So it's going to start very basic, but it will move closer and closer and closer to the things that we want to talk about over here, okay? But let's start with some very basic properties first. So in the slides, most of the slides you have are going to be minimal slides. They're going to look like this. And as I talk through things, they're animated. So you're going to see animations pop up that are not in the slides that you were provided earlier on. So do pay attention to the animations. So here is a select series of properties for a select series of atoms. You can see our halogens on top. You can see other first row atoms over here on the bottom. And we just want to draw a comparison between fluorine and some other substructures. Fluorine itself is very hard. It's a small element. We know that from, again, high school chemistry, first semester of your bachelor's chemistry. Very electronegative element, prefers to be anionic and not cationic. Tell me about the size. And so we already started this conversation. Oh, sorry, it's very electronegative there, so that's going to be a key property that we'll be discussing about over and over and over and over. It wants to pull electrons towards itself. So in terms of size, there's fluorine, neutral state, van der Waals radius, a little bit bigger than hydrogen. So in terms of a direct isosphere, not true. Let's dispel that myth right away. We're going to continue to dispel it over the course of the day. It is not the same size as hydrogen. We'll look at physicochemical data on organofluorine compounds that supports this argument also. It's actually closer in size to oxygen and nitrogen. So even though many times you can replace a hydrogen atom with fluorine, that just means the receptor, the enzyme, whatever the target is, has a little bit bigger pocket. It allows a little bit bigger of a substituent. Fluorine itself is a larger atom. Bond lengths, really important in medicinal chemistry, because you have your small molecule interaging with a target. How far away does your small molecule get from certain residues, from certain substructures in the biological target? The carbon-fluorine bond is notably longer than a CH bond. So again, let's dispel that myth that CH and CF bonds are the same size, same length. Okay, not true. It might happen that you can make that replacement. The CF bond in reality is closer in size to a CO bond. You see length close to a CC bond, right? So it is a longer bond, 1.4 angstroms there. Keep that in mind as we go through. Again, we'll continue to build on these concepts as we move forward. And so we can also look at the steric parameters. This slide talks about two different types of parameters, the Taft parameters and then the A values. Taft parameters, those are used for linear free energy relationships, so everybody's familiar with LFERs. your Hansch parameters, that would be one set of parameters that you've seen for understanding the electronic properties of substituents in an aero ring. Taft parameters differentiate steric and electronic properties. And here we're just looking at the Taft steric parameter and a series of substructures. You can see the R groups listed out there, HFOH, a variety of alkyl groups, and then some fluoroalkyl groups as we move down and down and down. And then on the other side, that second column, A values, that's the axial equatorial equilibrium that you've seen before for cyclohexanes. Typically, bulkier substituents prefer to sit equatorial, right? Nothing new there. Now we're just looking at specific data on how fluorinated molecules behave as opposed to non-fluorinated molecules. So let's go ahead and dig through some of this data and ask the question, how big is fluorine? So based on the Taft parameters there, fluorine is not the same size as hydrogen. It's behaving larger. It's behaving closer to a hydroxyl group in size. So again, that comparison between F and O in size still holds true. Let's look at methyl versus CF3. That's a huge difference there, right? CF3 behaves as a much larger substituent. So again, let me go back one real quick. So on the first one, fluorine versus OH, we're only looking at the Taft parameter there. We don't have the A values on this for the OH. When we look at this data, we can look at both the A value and the Taft steric parameter. Both cases, again, that CF3 is huge. It's big. If you're going to try to take a methyl group and replace it with CF3, you better have some space in that pocket, right, to be able to get it to fit. Or that pocket has to reorganize and open up, or something else has to happen, right? We know enzymes are dynamic, right, that residues can move, and so maybe it can open up and accommodate a larger, greasier substituent, but don't assume that they're the same size. So that CF3 group is actually more like a butyl group in size. So look at the parameters, look at the Taft parameter there. Kind of in between isobutyl and T-butyl in size. Symmetrical shape, it's going to have a shape more like a T-butyl group. Isobutyl, again, different shape, because one side's going to be large, unsymmetrical shape there with the isobutyl, but it's big. And same thing with the A values there, right? You can see the A value between CF3, look at the methyl, up there at 1.17, it's definitely bigger, okay? So it's a big element, it's a greasy element. Don't expect it to behave the same as a methyl group, okay? So again, dispelling myths. Here's another experiment, another set of data point demonstrating that the CF3 group is huge. It's way bigger than methyl. And this is going to be energy associated with rotation around a biaxial bond, right? So you have your biaryl. As you rotate around, you're going to come to a spot where the X group, whatever it is, has to eclipse with this hydrogen in order to spin around. And the energy associated with that is what we're looking at. And the bigger substituents are going to require more energy to push that bulkier substituent past the hydrogen when they're syncoplanar there, okay? So that's another data point demonstrating, again, that the fluorine and the fluorinated substituents are going to be much larger in size. So maybe, again, look at the data very specifically, hydrogen versus fluorine, you see a greater energy there. You see your fluorine, your methyl versus your CF3, again, a big energy difference. Using this type of assay, this type of experiment, the CF3 group is closer to a propyl group in size, definitely bigger than methyl. Okay. So we're starting to get a feel for the size of these elements. Hopefully, right at the beginning of the course, dispelled like one of the common myths that's just not true about fluorine chemistry and organofluorine compounds. Okay. So I'm going to pause. I've been speaking for a few minutes here, and I'm going to ask if there are any questions from anybody on these topics so far. Make sense? We're good? Okay. So we can keep moving forward, and we're going to look at some of the different types of intermediates that organofluorine compounds can perturb. So we've seen cations, we've seen anions, we've seen radicals. We know they exist as reactive intermediates. In some cases, they exist in biological systems. When we think about chemical stability, how these enzymes might be metabolized or decomposed in the physiological system, we're going to be thinking about reactive intermediates. And so that's the goal today, is for this, is just to start looking at very basic principles here so that we can build on them in subsequent days. We're not going to do everything. We're not going to get to everything in one day. So again, this is very basic, but we're continuing to build. So fluorine. Fluorine is the row with carbon, oxygen, nitrogen. Sorry, carbon, nitrogen, oxygen, fluorine. Sometimes in some of the lecture halls, there's like a periodic table right here I can point at, but not here. So then think about vertically, fluorine, you have your chlorine, bromine, iodine. Molecular size changes drastically as you go from iodine to chlorine. Fluorine to chlorine to bromine to iodine, right? And they change because the orbitals are different energy levels, and they get bigger and bigger and bigger, more diffuse, more diffuse, more diffuse. And it turns out that fluorine is the only one of those elements that hyperconjugates well with carbon-based cations or anions. If you think about chlorine and bromine, those orbitals are too big, too diffuse to overlap well with the carbon-based orbitals. So hyperconjugation is an absolutely essential principle for almost everything we're going to do for the rest of the course. We need to be thinking critically about how lone pairs of fluorines can distribute into, overlap with, and stabilize cationic species, alpha. In addition, we need to think about how anions will not be stable next to fluorine because you have a repulsion of electrons. Right? Fluorine pulls a lot of electron density to it. It has all these extra electrons. It's going to push away. There's going to be a repulsion, a destabilizing interaction there. That is something to consider. So those two properties are going to come up over and over and over. Those are hyperconjugative, positive and negative hyperconjugation. Fluorine does both of it. In addition, we're well aware of inductive effects. Being the most electronegative element, it's going to pull electron density towards it. It's going to pull electron density away from carbon. And as such, it's going to have an effect on cationic or anionic intermediates and the stability of those intermediates. So specifically, that inductive effect will destabilize cations. Here we're trying to pull electron density away from something that's already missing electrons. That's not a favorable interaction. In contrast, the anion stabilization, that's actually a good effect. If we have more electron density here, fluorine is kind of pulling its way. It wants more of that, and so that's a favorable interaction. A really key feature to recognize here is that these two effects, the hyperconjugative effect and the inductive effect, counteract each other. They work against each other. One is stabilizing, the other one is destabilizing. And so fluorine in some cases can help stabilize cationic species, but in other cases it can also disfavor cationic intermediates. And so there's this constant push and pull going on when you think about these reactive intermediates, and we're going to continue to build on that concept. Similarly with anions, you have a destabilizing effect through a hyperconjugative effect, but also a stabilizing effect through the inductive effect. And again, these contrasting effects work against each other, and sometimes we use one to explain another a phenomenon, sometimes we use the other to explain a phenomenon. Okay. So you have to keep them both in mind, that they're both simultaneously present in influencing the reactivity of substructures. So the hyperconjugative effect also is present when fluorine is attached to alkenes and or aromatic rings. So, pretend this might also be an aromatic ring here. You would still have a CsP2F bond. Okay, and we're going to talk about some of those as we move forward also. So the lone pair of electrons through resonance can push down, donate down, and present a full-blown anion. generate a species like this. It's not a great resonance structure. It is a true resonance structure, right? It is there, it is present. But think about the reactivity. That means we have partially nucleophilic character here. We have partially electrophilic character here. That's what's explained by our resonance structure. And so again, when we think about chemical reactivities, we might be able to exploit that for synthetic organic purposes. When we look at drug metabolism, we're going to talk about this property that fluorine can actually donate electrons into a ring while it's simultaneously pulling electron density out through an inductive effect. Counteracting effects again. And so let's see, what's next? CF3 group. CF3 is so much more simple. It really is an easy group to think about. There's no hyperconjugation. If you have cations adjacent, that's super destabilizing. Maybe a key number to think about is the electronegativity of CF3. The electronegativity of CF3. Anybody have a guess at that one? Yep, same electronegativity scale. Fluorine is 4. CF3 as a group, it's about 3.5. It's a lot, right? That's a pretty powerful electron withdrawing group. Fluorine wins, that's the most electronegative, but CF3, 3.5 is pretty powerful itself. And as it is so powerful, this can be a very, very strong effect. Show a couple of examples of that in the tutorial. When I start asking you all to give me some information, like you guys think about stuff, we'll see some examples of that. But it also, because you have a sigma star orbital in the CF bond, that's a CF3 group, and we're just looking at one of the sigma stars, an anion, vicinal, can actually donate into the CF bond. Okay, so the CF sigma star interacting with a p set of lone pair of electrons can actually be a stabilizing interaction. It can also lead to some degradation products that we'll see. Okay, so keep these in mind. We're going to continue to work with them. Maybe we can start to understand or see some data that we can use the different structures as rationalization for. That didn't come out right, sorry. So let's look at some data that demonstrates these types of intermediates. Okay. So first let's look at a series of pKas. That's fluoroform. You know chloroform. You use chloroform all the time, right? This is the fluorine version of chloroform. Look at that pK of 30. So it's acidic. It's not a normal hydrocarbon. That is acidic because you have this sigma withdrawing effect of fluorine. You have 3 of them building up, they're additive in nature. That's how we rationalize the pKa there. But if we use other perfluorinated hydrocarbons, so this one is like a T-butyl group that's perfluorinated there. Look at that pKa. Look how acidic that is, 11. That's super acidic, right? It's like a thiol. Why? And I've suggested in the figure why over on the far side here. When you have that carbanion stabilization, that leads to a more stable anion. The more stable anion, lower pKa, right? pKa is a thermodynamic process, thermodynamic property. More stable anions have lower conjugate acid or conjugate acids with lower pKas. So you can see that as we simultaneously build in more and more CF3 groups, this effect takes over, and you see this massive decrease in pKa. So it's really easy to deprotonate this guy. Think about the bases that might do that deprotonation. It's not going to take much. Yeah, you can use a stronger base over here to deprotonate fluoroform, right? Now the hyperconjugative effect is unique to fluorine. We said fluorine has orbitals of the same size roughly as carbon, and chlorine and fluorine don't. And you can see that in the trend that I'm going to show here on the bottom. So in the bottom we have fluoroform, chloroform, bromoform, and you can see the differences in pKa. Over here, the orbitals can, when we deprotonate, you would make an anion, and that anion has this repulsive interaction that's destabilizing. In contrast, when you deprotonate chloroform, you don't have this opportunity. So it would be easy to rationalize and say fluorine is a stronger electron withdrawing group, its electronegativity is greater. You would initially anticipate that its pKa would be lower than chloroform or bromoform. That's just not true. That's not what the data says. The data says that chloroform and bromoform are actually more stable anions. When you deprotonate, they make more stable anions, even though they're less electronegative. And again, we can rationalize that property by looking at this figure here and recognizing that there's a hyperconjugative effect by the fluorine lone pair donating back and resisting, repulsing against the anion that's formed there. So it's a cool thing. It's a unique thing. Hopefully, as we're moving forward, we're going to be thinking critically about these types of properties. And I just want some very simple systems to show them first. Okay? So I'm going to pause again and see if there's any questions or thoughts. And you're going to have to speak up because the AC is out here. So yeah, speak up loud. Yeah, the way I interpret that is that the chlorine still can hyperconjugate back a little bit. It's way, way, way less. But the chlorine orbitals, even though they're bigger and more diffuse, can do a little bit of this. And the bromine being even bigger and more diffuse can do even less of it. For this hyperconjugative effect, that's the way I would rationalize it. Okay.
The conjugative and hyperconjugative effects, we can actually quantitatively measure using quantum chemical methods. How much is the effect? What is the energy associated with it? How much is the overlap between the lone pair electrons and the sigma and the sigma star or the tau? All of those effects can be estimated quantitatively, and comparisons becomes much easier for interpretation.
Right. So there are, right, quantum calculations that would support many of these types of features. All of these orbital interactions can be replicated with molecular modeling at various levels of theory. Absolutely, you're right. Okay. So one more effect, and this is going to be relevant later, that hyperconjugative effect between an anion and a vicinal fluorine atom can be so powerful that you can actually see molecules fall apart. And you can see that CF3 group totally decompose. And it occurs through a fluoride elimination process that's shown here. If we think about taking this interaction to the extreme, that anion can go ahead and donate into the sigma star and fully break the CF bond. And when that happens, you get to fluorinated alkene type intermediates and you lose F minus. And that's a pretty stable anion, we all know. And so this is also a process that occurs regularly. There's one drug, trifluridine. I didn't think we have time to cover it because it's a pretty intense mechanism with how it interacts with systems, but it is a beautiful example to study. It's a place where organic arrow pushing meets complex biological systems, DNA biosynthesis, folate pathways. It's a really, really, really nice example. It does take a bit of time to talk through a lot of chemistry before you can even look at the drug. But it's a really beautiful system. Okay. So now we're going to start moving into biologically active molecules and thinking about chemical stability in a biological setting. So this would be a prototypical nucleoside, one that has been made, and a couple that have been made and studied before. Nucleoside-based therapeutics are super important, like antivirals, like one of the most important chemical classes for antivirals. You can see the structure there. You have your base, you have your sugar. Who's studied the decomposition of these, the chemical stability of these? Have you seen this in classes so far? You know that they exist, right? Have you thought about how they decompose? Because the chemical structure encodes everything you need to know about that decomposition pathway. Okay. So let's look at the data real quick. We have two compounds. Maybe we'll just look at the data on the left compound first. Let's just focus on the left. Okay. So this compound over here, or the pair of them, has that H versus CF3 over here. If we're doing nucleoside chemistry, we have the 1 position, the 2 position, the 3 position, 4, and then 5 would be the primary hydroxyl. So we're on the same page when I'm talking about 1, 2, 3, 4. So this would be a 3-trifluoromethyl group. The stereochemistry, I have it down for the purposes of teaching. It really wouldn't matter with the properties that I'm going to talk about here. The chemical stability under acidic conditions is drastically different. Look at the half-life, the decomposition for the non-fluorinated versus the CF3 variant of those, right? 20 minutes to 89 hours. Acidic conditions. So what I'm going to do, and then the same thing is true over here. So you can look at the chemical stability, H versus CF3. It's a slight variant. You have that alkene there. Chemical stability both at pH 2 and neutral physiological pH drastically changes as you go from H to CF3. So this is a little in-class exercise. And what we're going to do, like you have your page, right? So you're going to explain to me why. And so what I want to do is give you guys about 2 minutes. I'm going to give you a hint. I'm going to give you another 2 minutes to keep developing your answer, and then we're going to talk through it. Okay? So initially work on your own, but we're going to come back all together as a group and talk through it in just a minute. But there's the problem right there. Explain that. In your slide decks, when I give you guys the slides, and I think they were circulated, you have an extra blank slide. So I've given you a little bit of extra space if you need to work on the slides, if you have those printed or in your iPad. But here you go. And I'm done for a minute. Okay, so tell me, what's the first step of this process? We're going to talk about mechanism because we're organic chemists first and foremost, or I am. So what mechanism is this going to go by? It's acid stability. I'm going to wait. This is going to be weird until somebody talks. I can wait a long time. So in the presence of acid, what's going to happen here? Acid-base reaction, right? So where are we going to protonate? What's our most basic position is going to be over here on the heterocycle, right? We might think about protonating a basic heteroatom on that heterocycle. So maybe we might want to think about a structure that looks like that as the first step. And you might be able to think about other spots on the heterocycle there. Oops, I actually changed the heterocycle miraculously. Sorry, when I made my other figure. That was my mistake. Then what? What happens next? There's a key reactive intermediate. Do we have any glycochemists here? Sugar chemists? No, not exactly. Okay, so this is fundamental glycochemistry right here. You have a leaving group. Think of this big thing. What if we just said this entire thing is Lg, a leaving group? Then what do you expect? What if it's a chloride? What would you expect? Maybe we might want to think about a vicinal heteroatom that has a lone pair of electrons. And if we borrow the electrons from oxygen to push off our leaving group at the alpha position, we make that intermediate. Now we have an oxocarbenium ion, right? We have a double bond right there. Letting people think. I'm deliberately pausing, letting people think. I see you pointing and talking to your friend. Okay, so if we have the fluorinated functional group X, how would that perturb the stability of the cationic intermediate? That oxocarbenium ion is a structure for which we put the formal positive charge on oxygen. But is that the site where nucleophiles will react? Do they react on oxygen? They react at carbon. So even though we think about an oxocarbenium ion as having a formal positive charge here, this looks more like a carbonyl structure, doesn't it? It's like, think about it like a carbonyl with a Lewis acid or something coordinated. You would still react that at the carbon atom, and you have the same thing here. Instead of a Lewis acid, you have a carbon-carbon bond, but our oxocarbenium is intrinsically electrophilic on carbon. And now let's think about how the fluorinated substructure perturbs the stability of that oxocarbenium ion. And so that oxocarbenium ion would have a sigma withdrawing group. If it's fluorine, if it's a CF3 group, we would be pulling electron density away, making delta plus character over here, but we already have delta plus on the molecule. We have an electron deficient species. We're trying to pull more and more and more electron density away from it, and that's a destabilizing interaction. And that explains this data that's shown up above. If we have H, we can go through this protonation and the formation of the oxocarbenium ion. That occurs really easy for H. But you put that fluorinated group on there, and it's much more difficult. And hopefully you're seeing why we need to think about analyzing, why we need to use those reactive intermediates, understand the perturbations, the sigma withdrawing effects, and some of the other effects as we move forward. Okay, so the CF3 group would destabilize the cationic intermediate. Make sense? It's a powerful effect, isn't it? That's crazy. So, part 2, this one's going to be a little bit quicker. I'm going to give you just maybe 2 minutes to work on this. You can talk with your friend. How would you compare those two on the bottom? You can see the placement C2 versus C3 of the nucleoside. And go ahead and work on that one for just a minute, all right? Okay, we got it figured out? So first I'm going to ask, everybody has to vote. If you don't vote, no tea at the break, okay? So you have to vote. So we have 2 structures. I'm going to point at this one and then point to that one. Who thinks this one is more stable towards acid? Hands have to come up. This one more stable? This one? I don't see enough hands. There's a lot of people who aren't getting tea. And it might be tomorrow too. I'm a parent. I can be pretty tough. Okay, so let's do this again. I want to see more votes, okay? So this one. So I think group thought a couple more hands came up. So people are still not voting. It's your right. You have to vote. Okay, so is that a joke? Okay. So here we have our 2 structures. I would be voting for this one. I know the secret. Some of you know it too, apparently. So we need to think about the power of the inductive effect. And is it more powerful when it's closer to the cation or further from the cation? And that's the principle that we're looking at here. So again, we'll be making the cation. We'll be forming the cation here at this position. On one structure, the CF3 will be 1 CC bond away. On the other structure, that would be 2 CC bonds away. And so it's a more powerful electron withdrawing effect when you're closer to the cationic center. So this one will be substantially more stable than this. Again, the bases are slightly different on these structures, but you'd expect this to be outrageously stable. And there are actually some FDA-approved drugs that do have a CF3 group at that position. Sofosbuvir would be one of them. Sovaldi is the trade name, and that was approved, I think, in 2015 for hepatitis. Has a methyl group and a CF3 group, both at that position right there. Okay. So chemical stability, acid stability impacts drug discovery. Why? So where would a drug experience pH 2? GI tract, right? You take an oral medicine, acidic in the stomach, neutralizes as you go further down the GI tract, but initially that stomach acid can decompose. We can stabilize it chemically. There are pharmaceutical strategies for stabilizing compounds, avoiding specific pills formulations that don't degrade at pH 2. They'll degrade at more neutral pHs, right? We have some special coatings and things like that. How else can we avoid stomach acid? Huh? Yeah, so if we use some type of a sub-Q or an IV injection, we can avoid the GI tract. There's certainly plenty of drugs that will inject when needed. Not always the easiest for certain types of patients, but certainly something we can do when needed, okay? But there might be strategies to use fluorine to avoid these acid-sensitive moieties, okay? So let me pause again. Any other thoughts or comments or questions here? Let's move into some other cool properties. Oh, yeah, sure.
It would be actually quite fun. Instead of CF3, the right hand side, that is much more stable towards acid. To replace CF3 with fluorine, let's say, things will be altered, right? Then the hyperconjugation might take the front seat as compared to the inductive effect.
Can I use this too?
Yeah.
Is that okay?
It's hypothetically I'm saying that.
Yeah, so
even if the structure doesn't exist, or I don't know.
So we'll be looking at this, and you're saying, what if you have fluorine there? So if you have, so I would argue that this is also going to be I was looking for a laser pointer, but I'm on a chalkboard, so I can't point at this. So I would also argue that this will not hyperconjugate. No. So it's one too many positions, right? If you had fluorine, where did I put my chalk? Oh, it rolled back. Okay. So if you had, fluorine here, then we could think about hyperconjugation in, but being one position over. So being one position over, we only get the inductive effect. So.
But the unsaturation one over there.
Oh, the unsaturated one might be different. Yeah. So that could probably.
Use extended hyperconjugation.
Yeah. Yeah. So if you had, right, this, then it depends on which position it is, right? So if you had fluorine here, then you could hyperconjugate in, and that would be stabilizing.
Yes.
But if you put fluorine here at the 2 position, destabilizing because it's inductive still.
That would be a dramatic increase from, when x equals to h, that is less than a minute. That might actually go.
Yeah, this one, right, this one, if you had fluorine there, would probably be difficult to isolate, purify on a silica column, right? Yep. So that's another good example to think about for sure. Think about your arrow pushing with organofluorine compounds. Think about those hyperconjugative effects. The positioning of that fluorine atom does matter. Yep, absolutely. Okay. So we're going to talk about a couple more properties of fluorinated compounds. And so another important property is solubility. And so this is a really beautiful system. This is a system in which you have water, some lipid hydrocarbon, octane, hexane, maybe your step funnel, and you have a fluorocarbon. And it turns out that you get a triphasic mixture. So the fluorocarbon hates water and it hates octane, hexane. Does its own thing, totally. And it's dense. So this hydrocarbon is very dense. It doesn't like water, it doesn't like the hydrocarbon, it does its own thing, and maybe we can understand why when we think about really basic intermolecular interactions and the structure of these fluorinated compounds. The representative example we're looking at, it's here, it's an octane per fluorooctane. The properties we're going to talk about are true for many different types of fluorinated compounds. Oh, sorry, that's a hexane, my bad. So it's a fluorinated hexane. So the fluorocarbons have terrible water solubility. And it goes back to some very basic principles of fluorine and the electronic structure. Let's think about the scaffold. The fluorine atoms being so electronegative are pulling a lot of electron density away from the carbon. And that leaves the carbon all across the molecule. All the carbon atoms are highly cationic. and the fluorine atoms are anionic. So it gives you this type of structure in which you have extra electron density. It's kind of shown by electrons. I'm trying to show just extra electron density on the shell of the molecule and cationic character in throughout the middle. Okay, and that has high chemical stability, as we saw earlier. Now those fluorine atoms, they have extra density. How do fluorine atoms hold the electrons in their lone pair of electrons? Are they good at releasing the electrons out? Or the electronegativity makes them want to retain those electrons close? And the second is true. So fluorine, being so electronegative, pulls its electrons towards itself. When it pulls electrons towards itself, they become less basic. So fluorine, when you have lone pair of electrons on fluorine, those are not very good bases for hydrogen bonding interactions. Okay, now what I'm saying is extremely true for intermolecular interactions. There'll be a different story when we start talking about intramolecular interactions. So fluorine can do intramolecular hydrogen bonding, and we're going to show several examples where that's important. But for intermolecular hydrogen bonds, fluorine is very poor as serving as a base in those interactions. So we can look at this figure again, the schematic on the bottom. Here's our representative fluorocarbon, again trying to show the fluorine atoms on the outside that have the extra electron density, but they don't want to share their electrons. They don't want to engage in hydrogen bonding interactions, so they are not good at hydrogen bonding with water. And that's the predominant driver of water solubility. For something to be soluble in water, even if it's a drug molecule, for something to be soluble in water, it's hydrogen bonding with water that solubilizes it. Okay? So fluorous compounds, really bad at these types of interactions. They're biphasic when mixed with water, and that's what's going on here. The aqueous and the fluorocarbon layers are separate. Now, when you think about the hydrocarbon layer, maybe you might think, gosh, why doesn't it dissolve in hydrocarbons? And well, let's think about why hydrocarbons exist as solvents. They certainly have lower boiling points than things with a lot of hydrogen bonds, but we still have these London dispersion forces, these transient dipoles that exist in the hydrocarbon just because the electrons are migrating around and they happen to kind of drift over to one side. Oh, now we have a little bit of carbocationic character over on this side. And so these London dispersion forces are very important. Intermolecular interactions in hydrocarbons, but those do not exist for fluorocarbons. In fluorocarbons, the fluorine atoms are holding on to the electron density so tight, and those fluorine atoms are so hard, that you do not get this random London dispersion force type distribution of electrons. Those electrons really do stay tightly associated with the fluorine atoms, so while the hydrocarbon might have these transient dipoles, the poor polarizability of fluorine and the carbon-fluorine bonds means that they don't respond. They don't similarly make these transient dipoles, and so you actually get very poor intermolecular interactions between fluorocarbons and hydrocarbons. And that's the reason why these fluorocarbons don't mix with hydrocarbons particularly well either. Okay? So it's a cool phenomenon. It's unique. But recognize that many of these carbon-fluorine bonds do not engage with water. That's going to be really important, again, as we move forward in a couple of days, really Wednesday. So let's look at a couple of other properties here. Maybe the first property, I pointed it out already, but we can recognize it quantitatively on this side is thinking about the density. And so for this comparison, we have our hexane. We have a partially fluorinated hexane. So 111, 222, 33 fluorinated hexane, and then there's perfluorohexane over here. Look at the density of those, pretty drastic. Water, 1.0, the number we all know. So the hexane itself, not very dense, high density. And there's a lot of mass there. The fluorine is heavier than hydrogen, so per unit, yeah, you would expect that to be more dense. That makes sense, right? Okay. So another really cool feature, unique feature of these fluorinated compounds is that they're really light, but low boiling points. Look at that series. Boiling point of 57, hexane about 70. Why is that? Most people, when we think about boiling points, we think about a couple of things, like hydrogen bonding interactions, like water, right? Of course, that's something we think about. But we also think about molecular weight, right? So it'd be easy to start to say, oh, it must be a molecular weight thing. And it's obviously not in this case when you look at the weights there, right? 338 versus 86. That doesn't correlate. Okay. So we've dispelled one rationale for why compounds are typically higher boiling or lower boiling than others. Maybe another thought might be, well, maybe it's the dielectric constant. If you have something more polar, those molecules might, engage in, and that's not true in this case. So again, the fluorocarbons have very low polarizability. The dielectric constant, like these are less polar than hexane. Look at those numbers. That's crazy. It's cool the way that compound 2 is polarized, like almost 6. That's nerdy cool, right? So, you have the CF3s there and the CF2s, they're pulling electron density to the left. Over here with the CHs, they're allowing the electron density to go over towards the perfluorinated side, so you get this dipole. So that's a pretty cool feature there. So that has a good dielectric constant. And so ultimately, how do we explain this? We have to think about the intermolecular interactions again. And how strong are the intermolecular interactions between the perfluorinated carbon when it engages another perfluorinated carbon? And what you end up having is this repulsion almost. So again, we talked about this electronic structure in which the CF bonds pull electron density away from the carbon. You have this anionic kind of shell around the molecule, and those, when they engage each other, don't engage very well. There's a bit of repulsion there, and that's why you see this low boiling point. The solvent doesn't want to stick together. It wants to allow itself to go different directions, okay? So, moral of the story here, these fluorocarbons don't like much. That's why, one of the reasons why we use them on all types of materials. If you have waterproof jackets or bags or non-stick pans, you put a fluorocarbon on it, nothing sticks to it, right? That's why they're so easy to clean. That's why, if you spray your hiking boots with them, water doesn't get through. Water hates fluorinated carbons. Now, we've done that in society at the detriment to ourselves for health reasons, right? PFAS can build up in tissues and they're toxic. The environment, we're finding a lot of environmental pollution, but they do work chemically for a lot of purposes. For better or for worse, maybe we can start to understand the whys those work, even outside of medchem. So with that, I think this session I'm going to put on a pause. The next session that we have is going to be a lot more problem solving. So when we had some of those in-class exercises, we're going to do quite a few more of those. And we're going to come back and we're going to keep teaching and teach at a deeper level all of these things. So when we come back, when we reset, I don't know how long of a break we're going to have, but we will be ready to be thinking, be ready to working on your own, and then we'll have some little small group work too, okay? So we'll see you all in a little bit after the break, but I'm not sure exactly how long that's going to be. So we can take a short break for a few minutes and then come back and introduce the tutorial.
Yeah, so I think it was very wonderful. I'm sorry we should have had some of these friends who shared this information with them yesterday. But yeah, so I think we are going to get these things printed now. And so I think in the next class onwards, all college material will be printed so that they have something to take notes and work on those exam. Okay, so we will take around 15 minutes.
15 minutes, so that's 11:20. Come back 11:20.
Yes, I will.
Giving me more chances for questions. Yeah, definitely. As soon as I give you guidance, it's really funny, right? Maybe they talk for a little bit. Yeah, I think that may have better appreciation. That's the thing I have also told you, but my students are also very good answers. So I'm asking everybody needs I think you are here. I also want all my students 10 of them came for recording that six somehow. Yeah, I know that. Absolutely. I mean, that we also felt so bad. We were worried for that only we came.
We can come in second my office there.
Yeah. I was thinking that I will go quickly to all this. Let me do one thing. Some minutes of the interview. But it's actually fun, you know, sitting here and discussing different way we are looking at, because I remember when I joined my PhD. My bit mistake. My bad.
Very simple. Set the bag over the laptop over here.
So you have the problem solving session or this is guide?
So welcome back, everybody. We can get going again. And so now it's time for you all to get to work. Okay. So you have your paper, you have your pen or pencil, you have your brain turned on. You got enough coffee or tea or caffeine somehow in your system so that your neurons are firing pretty quickly. You're all amped up. What our goal here now in this session is to get you all thinking more deeply and quantitatively in many cases about the power of these perturbations in chemical reactivity and how impressive, impactful they are. We saw in the previous session, we were talking about the nucleosides, half-lives of minutes going to hours. And there are some other, that was the nucleoside example, so as the oxocarbenium ion. There are also perturbations in simpler systems, and maybe we can start to look at those. As much as possible, our goal is to think just critically about the physicochemical properties that are perturbed by fluorination. So this is just a reminder that we're still building very basic properties into your minds, get you to think critically about them so that we can apply them later in more biological systems. So these are two problems, actually 3 problems there. 4 problems. I can count 1, 2, 3, 4. Okay, so there's 4 different problems there. We're going to do them sequentially. And so in the first problem, we're going to look at this compound here. You can see a tosylate. Tosylate's a good leaving group, right? You might think of that as like a chloride or something like that as a leaving group. In this system, we're going to look at a solvolysis reaction. Solvolysis reaction, you heat it up in an alcohol solvent, heat it, let the leaving group leave. Leaving group leaves on its own, makes a carbocation, then the alcohol would add back in. So in that type of reaction, it's like an SN1 reaction, that's what we would classically call it. Rate limiting step, formation of the carbocation. Carbocation stability is going to influence that step. So what we're really looking at here is stability of the carbocation, and we're going to specifically think about a system in which we have methyl groups and CF3 groups. So the question I'm posing to you is, what's the difference in rate in solvolysis if you have dimethyl versus CF3? Give a quantitative estimate. And when we're giving these quantitative estimates, we're thinking about orders of magnitude. This isn't 2-fold or 5-fold. This is 10-fold, 100-fold, 1,000-fold, 10,000-fold. What's the difference in rate of solvolysis, do you think? So I'm going to give you a couple of minutes, maybe 1 minute, in your head. How powerful do you think that effect is? 1 billion-fold. 1 trillion-fold, 10-fold. You guess. Okay, so you got a guess in your mind? You got an answer? We're going to do a little bit of multiple choice again. Okay, take your answer in your head, and what's it close to? What's it closest to? And you can see how big and bold we're going here. 10 to the 11, that's crazy, right? And 10 to the minus 9, that's crazy too. Okay, these are crazy big numbers. Or it might be closer to 100 or 1,000, either way. So who votes for A? B? Okay, everybody's voting here, okay? You guys didn't listen to that last time. Everybody's voting this time. So A, B, C, D, E. Ooh, E is same rate. This course would not work if those were the same rate, right? That would be like, okay. F, G, H, Okay, scared you off of all the inverses there, right? Because why? The electron withdrawing effect is going to destabilize the carbocation, right? So this is the property that we're predominantly thinking about. How powerful that effect is. So let's go back to our guesses here. Wow, okay. And so we can also look at the next one too. I didn't necessarily assign this one initially, but this is a protonation reaction. So this would be like in a HX addition to an alkene. You add the proton, you make a carbocation, and then that whatever the X group adds in, hydrochlorination, hydrobromination, those types of reactions. And so similarly, we would protonate this position, hoping that the benzylic resonance stabilization will facilitate the process by stabilizing the carbocation. In that case, the methyl group versus the CF3 group, 10 to the 10 difference in rate. That is how powerful that effect is. That terrify you all yet? Okay. Pause, questions, comments? It was way beyond your expectations, right? It's a powerful, powerful, powerful effect in perturbing reactivity. Let's do the bottom set, okay? So we're going to go to the bottom set. You can see those are just SN2 reactions. Soft nucleophiles, good electrophile, so this would just be iodomethane. Bromopropane, right? It's ethyl, but it has an extra carbon there, so that'd be 1-bromopropane. Do an SN2 reaction with iodide or a thiolate anion. And the question here, the goal here is to estimate what's the rate difference. Again, 10-fold difference, 100-fold difference, 1,000-fold difference, 10 to the 10 difference. Okay, what's the difference in rate for maybe this series and that series? So I'm going to, again, give you all a few minutes to work on it yourself. Jot down some things on your paper. We'll look at the actual data in a couple of minutes. We're going to do this in 2 phases. I'm going to give you 2 minutes to make an estimate yourself. Then I'm going to give you probably 2 or 3 minutes to work with your partners or your friends next to you so you can talk through the answer real quick, and then we'll come together, okay? So I'll let you know when to switch from individual work to group work, okay? Take a minute, a couple minutes. By yourself first. But first you make an estimate by yourself, and then you share your answers with your friends after that. So right now you make your own estimate. Okay. scientist, master's level, PhD level, you need to be an independent thinker. You can't always rely on your friend next to you. Collaboration is good, interaction is good, but you think about it first, deeply, and then share your answers, just as a strategy about going through your career. So that's why I want to do it this way. On most of these questions, you work yourself first, and then we go collaborative setting. Okay, so yeah, talk by all means.
Maybe it should be okay for first year masters, right? Some hints maybe after 2 minutes, 3 minutes.
Okay.
I just not done this SN1, SN2 reaction.
Okay. So we know SN1, SN2. What's that intermediate look like? What's the intermediate look like for SN2? Nucleophile attacks while the leaving group leaves. You go from sp3 hybridization to sp2 in the transition state, back to sp3 as your product continues to form. That concept is going to become relevant in just a minute. Let's go ahead and get initial estimates. So maybe for the CF3 group, we can do a quick vote. You see the choices there, you got a feel for it. Okay, so we're going to do the same thing. A, B, C, D. Oh, there aren't many people voting for this. Okay, we're going to start again. Ready? A, B, C, D, E, F, G, H. Okay, so we have several different answers here. Let's go ahead before we answer that, maybe do another one. I'm going to show you all the answers in just a minute, but let's go ahead and do this one here. This is another CF3 group, but the CF3 group isn't directly adjacent, it's a little bit further away. So again, how powerful is that effect? Did you have a chance when you were working on it before to kind of work through both sides of this question? You have it, you made, I see some yeses, okay. So what about that one, A? Again, the CF3 group is a little bit further away, and we already talked about how the inductive effect is a little bit weaker as that electron withdrawing group goes further and further and further away, right? So we would expect this one to be maybe a little less powerful. So A, nobody's going for A this time. B, C, C's, okay. D, some D's, okay. E, again, if we have E, we're in trouble for this class, because if the fluorinated compounds behave exactly like the non-fluorinated compounds, then fluorine chemistry isn't special, right? Okay, so E, F, G, H, and we're done. Okay, so Let's see, you want to see some answers? You ready to look at what the data says? The papers are down there on the bottom, so if you ever want to look these things up and find the original data, I've tried to always provide that for you. But there's the powers there. We're going to talk through it a little bit in this first series here. The CF3 group being attached, 10 to the minus 5, maybe 5.7, so maybe it's closer to 10 to the minus 6, but you can see how powerful that effect is. If you put a CF3 group in the vicinity, CH2 and then your CF3 there, it's 100,000-fold change, 500,000-fold change in reactivity. It's a massive difference in chemical reactivity from that functional group. And that decrease in activity from the CF3 group, it's additive. I mean, when you look at the contribution of each fluorine atom, 10 to the 2, 10 to the 3, 10 to the 5, you see it build and build and build. And on the other side, if you remove that CF3 group 1 unit away, you still see a reasonably powerful effect, 10 to the minus 4. That's still pretty significant, right? 10,000-fold different rate. If I have a reaction and it runs for an hour with a non-fluorinated, and then I do the CF3, am I going to really wait 10,000 hours for that reaction to finish? That'd be pretty tough to do, right? That'd be forever. So we need some different types of reactions to get some of the fluorinated compounds to behave properly. If we're trying to do an SN2 chemistry with this CF3I, we're going to need some catalyst or heat it really, really, really high, or do something else to get that reaction to work, because it's not going to be fast. Okay. So you see these fundamental differences in reactivity. One of the reasons fluorine chemistry is specialized, synthetic organofluorine chemistry is specialized, because when you put fluorine on organic molecules, they don't behave the same way. You need specialized reagents, specialized conditions, specialized catalysts to be able to get these types of reactions to work properly. So pretty powerful effect. Again, that effect is generally an inductive effect. So in the SN2 reaction, we start with sp3, we move in the transition state to this sp2 hybridized carbon atom. sp2 hybridized carbon atoms are more electrophilic than sp3 hybridized carbon atoms. As you go from an sp3 that has a lot of p character, sp3, one s 3p orbitals contributing to the sp3 orbitals in the hybridization there. An sp3 carbon allows the electrons to release down those sp3 bonds. They're longer bonds, we know, so those electrons are allowed to go further away from the carbon center. In contrast, when you have an sp2 hybridized carbon, one s orbital, two p orbitals, the hybrid sp2 orbital, it's a little bit closer to the nucleus. Carbon wants to pull the electrons a little bit more closely to it. Okay. And so the carbon, because it has these shorter sp2 bonds, where's my cursor? I'm going to switch. Because we have these sp2 bonds and they're trying to pull electron density towards themselves, is the CF3 going to allow that? CF3 is pulling electrons towards itself. It's inductively pulling electrons towards it. When this goes to the transition state and you have a CsP2 hybridized carbon atom, it's trying to pull electrons back towards itself. There's an electronic pull and tug of war going on between the electrons there. So this intermediate becomes destabilized in the transition state. You get a high energy transition state, then you get the slower rates that you see here. So it's not a full-blown cation, but you're still going through an sp2 hybridized transition state, and the electron withdrawing group is destabilizing that state. Okay. It's So it's a cool phenomenon there, powerful phenomenon. Maybe we can move on to another chemical reactivity problem. So this is another reaction for you to try. This is what type of reaction? I'm going to let you think about it for maybe 2 or 3 minutes. I'll give you a suggestion of what type of reaction, as I heard you've been doing some simple reactions of this type in the last few minutes. I was told in the last problem that you guys are doing some of these in your class. So I'm going to let you work on this for 2 minutes, and then I'll give you a hint, and then I'll let you continue to work on it. Okay, so what type of reaction do we think this is? We have an alkyl compound, aliphatic compound with a couple of bromine atoms on it. There's some fluorine atoms too. CF bond is usually pretty strong. It's not always the easiest to break that. So 2 bromine atoms on a carbon. We have a phenol. What's that phenol going to be? Phenols can be nucleophiles. Carbon-bromine bonds can break in substitution reactions. So you just learned SN1, SN2, as we heard. So maybe we're thinking about like an SN1 or SN2 type reaction. And specifically, this question asks you to choose which of those bromine atoms will get replaced. And they're in chemically different environments. One being alpha to an F, the other one being alpha to the CF3. Which one of those is more reactive, and then why? That's what we're really trying to get at. Which is more reactive and why? So now you can really start to think about the detailed intermediates and the stabilization and destabilization with that hit. Okay? So we have an SN1 or SN2-like reaction of the carbon-bromine bonds using a phenol nucleophile. What products are going to form predominantly? Do you want to see some representative answers? I just drew up a couple. Maybe you drew some other things. Let you look at those for a minute. Perhaps those were similar to some of the answers you might have been thinking about already. So it's a little bit more of a hint. I'm going to let you keep thinking a little bit more. Yeah, I'm going to let you keep looking at it a little bit more. You've had a chance? You've thought about it? We're going to vote again. There's only 3 answers this time. It's going to be easy for me to go through them. I don't have to go from A to H, so it's only going to be A, B, or C. So let's go ahead and do our survey. A? B? A lot of B's. C? A few C's. Okay, so nobody likes A. I agree with that. A is bad. Fluorine is not necessarily a good leaving group. Okay, when we think about leaving groups, you think about things that have stronger bonds to carbon are going to be worse leaving groups, just for simple SN1 and SN2 like chemistry. There are other ways to make fluorine atoms leave, but we're not covering that necessarily right now. So B and C, there seem to be more B's than C's, and I agree with that. B, yay. Whoever got a B, give your friend a high five, fist bump, handshake, whatever you want to do, but a little celebration there. I got one right. Good. I think based on the first 2 questions, we weren't doing very well on the 10 to the 10, 10 to the 18 questions. Those ones were pretty tricky, but we got B, and that's good. Why? That's the question, right? The basis of understanding this question is the why more than it is I got B instead of C. So maybe we can talk about some of the basic principles behind the reactivity and why B is a correct answer. So there are 2 principles. Maybe I want to talk about the one on the left first. So in this system, we have the fluorine atom adjacent to the bromine atom, and on the left there I showed the hyperconjugative effect. So fluorine bearing the lone pair. Sorry, I don't know where my mouse went. There it is. Okay. So fluorine bearing the lone pair of electrons in the alpha position can donate into the carbon bromine sigma star and push off the bromide. Okay. And we can get a resonance structure. That resonance structure would look something like this. Full-blown positive charge on fluorine is not the best resonance structure, but it is a resonance structure. It does demonstrate a little bit of a perturbation in reactivity. So in this system, the bromine is predisposed to leave. The bromine is already has a weaker bond between the carbon and the bromine. This structure also shows that there's a little bit more delta plus character here. But it's intrinsically electrophilic at that position. So this arrangement, one fluorine atom adjacent, geminal to the bromine, is activated. At the same time, the other position is deactivated. Okay. And you can see that there, the CF3 has a really strong sigma withdrawing effect. When that happens, the carbon lacks some electron density. It will pull some of the electron density in the carbon-bromine bond towards the carbon. Then it becomes more difficult to break that carbon-bromine bond. Remember, for this SN2 reaction, bromine needs to pull all the electrons away. It needs to tug all those electrons towards itself. And the CF3 is doing the opposite. It's actually making the carbon-bromine bond drift closer to the carbon. Okay. So you have 2 effects here. You have the sigma withdrawing effect, decreasing the reactivity of this position, and then you have the alpha fluorine atom activating the other position. But you can see how those basic principles that we were talking about early on are becoming relevant in the synthetic chemistry and chemical reactivity. Okay. So that's just a second nice example there. Any questions?
So I wanted you to also ask them about stereochemical outcome.
Stereochemical outcome. So if we have, say, So what would the product be for that? I mean, it had the same connectivity as B, the stereoisomers would be. We'd have to make a choice there. So what would you get? I want to see you guys drawing it out real quick on your own paper. I just drew the part of the molecule that's not reactive, so no secrets there. But we'll need to make a decision here about what happens over the other carbon, right? So we said this is going to be what type of a reaction? SN2, right? I can't do 2 and hold the chalk at the same time. So SN2 type reaction. What's the stereochemical outcome from an SN2? Inversion of stereochemistry. So that would be one answer. If you have rotation around the carbon-carbon bond, you could also draw that same stereochemistry from a different angle, right? I won't make you do R's and S's. You don't need to do that right now. When you do R's and S's, though, remember fluorine takes priority over oxygen, right? Okay, cool. You move forward over here? Yeah, let's go forward. Here's another fun one. So this is from a recent publication. This one comes from my group, so I know all the secrets to this one. So this is a series of substrates that will be subjected to DDQ. This is a chemical oxidant. There are a couple of different mechanisms by which DDQ can act. I'll give you a hint about what that reactivity is in just a minute, but first I want to look through the data and just make sure you understand the nature of the question. So in this case, we have a styrene substructure, aryl group with a vinyl group attached to it. That's a styrene. That substrate oxidizes to make the arene under mild conditions, 50 degrees C. Not too bad. Hot day in the summer, right? Really, really, really hot day. Okay, miserably hot day. If we replace the aryl ring with a CF3, maybe have something else over here, that temperature jumps. You have to heat it a lot to get that oxidation to work. It works well, 95% is great, but you have to put a lot of thermal energy in it to get it to work. If we switch out the phenyl ring and instead introduce a T-butyl group, nothing happens. NR, no reaction. Chemically inert. When I say no reaction, that's like 0% conversion. We re-isolate the starting material. Sometimes you heat a reaction a lot and it like degrades. You get 0% yield because everything fell apart. The molecule just decomposed. In this case, the molecule is stable. So we need a chemical explanation for why there's this difference in stability in the various molecules. Now I'll give you a hint. One of the mechanisms by which DDQ acts is by ripping off H-. It can also behave as radicals, and there's experimental data in the literature that supports either mechanism based on what substrate you have. So sometimes with some substrates it behaves as H-, an H- abstractor. In other cases it behaves as an H. abstractor, so it does radical chemistry. For this example, we're just going to look at DDQ as a hydride ion acceptor. So I'm going to give you a minute to think about the different intermediates. If you abstract H- from the different positions on the molecule, which ones are more stable, which ones are less stable? And then we'll have to think about the perturbations imparted by fluorine as you continue to develop your answers. So this is a tough one. This is a tricky one. There's a lot going on here. There's several different examples. Perhaps the best place to start is just to think about the first one. If you take H minus off of any of these positions, why is this one so stable? Okay, so start on that one. I'm going to give you like 2 or 3 minutes, and then we'll kind of keep talking through it step by step by step. Okay, that's the first one. Okay, so we could talk about why the first one is so easy. 50 degrees C. Let's go ahead and look at that structure. The hydride can be abstracted from 3 different positions. Perhaps more, but I'm really focusing on 3 because I know the answer, right? So, you can take a hydride from C3, C4, or C6. Those are going to be the ones that are activated. And they're activated because those are the positions, particularly the C3 and the C6, that are adjacent to the alkene. So let's go ahead and look at what happens if we abstract a hydride, maybe from the C6 position. We get to a carbocation there. Is that a stable carbocation or a not stable one? It's okay. It's pretty good, right? It's allylic, and we think of allylic stabilization as being good. In this case, pretend we do one here. Is that a good hydride to take off? It's secondary, right? Secondary position, not great, not anywhere near as good as the allo, but it's okay. Yeah, maybe in some systems we might think about it. Not the best in this case. What about that one? That's awesome. That's amazing, right? Because you have the allylic stabilization. But you put there your carbocation there, now it's benzylic, so you can draw resonance structures that delocalize the cation all the way through the system. So that's really awesome. Okay? So that would be a simple walkthrough for why the first example there is so stable. Okay? So repeat that thought. Go through and rethink that logic, that sequence of logic for the other 2 examples on the top. And then we'll come back and answer the question more fully in just a minute, okay? So keep thinking about that. There's a lot of structures, a lot of positions to think about, so I'm going to give you a little bit more time. Okay?
So there could be a mixture of product also which is possible, right, for plastic pieces, or it's a single product. It's about 95% is isolated. Yeah, that one. No extra. Yeah, so, right, so this is from my work. And that could be isolated by yeah, the distance also side by side. So that looks pretty
Do you want to start thinking about the answer to that? Should we start working through it? Okay, so let's go ahead and jump forward. Oops, my animations didn't do exactly what I wanted. Okay, so first of all, let's go ahead and think about let's calibrate ourselves at what we're looking at here. We have our, on the top, 3 model systems in which we go from phenyl to methyl to CF3. So we're just trying to understand the power of the CF3 group versus methyl versus phenyl. On the top series, we have phenyl, 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 and those are kind of modeling this position. On the bottom, we have T-butyl, T-butyl, and T-butyl, so they're modeling this system over here. Okay, that's just to calibrate everybody on what's going on and where we're going to go. Now, in order to explore this computationally, we did quantum mechanical calculations. I don't think the level of theory is shown on here, but it was a B3-lip based calculation. When we remove hydride, it takes energy to make that carbocation. So that's what the calculation is estimating. What's the energy associated with taking that hydride, removing it from the molecule, and leaving a carbocation? So for the first compound, the first model system, you can see the energies here, calculated energies. 219 kcal per mole. That's the one that we drew up before and said that's like a really stable one because you're conjugated here with the allyl group, but it's also a styrene, so it conjugates all the way through the aromatic ring. Very stable carbocation, easy to remove that hydride. Definitely a good first step for this overall oxidation sequence. As you look around the molecule, we also noted before that the C6 position was okay. That'd still be an allylic cation, so maybe that's reactive enough, and the calculations say the same thing. Not as good as the other position, but when you see the other numbers, certainly within the range where you could get some reactivity at that position. Now, this model system is a little bit different than what we had here for the example from C.J. Lee's group, but we are also estimating the benzylic position, 228 kcal per mole. Again, if we remove that hydride, we get a benzyl carbocation. It's still pretty good. So as you look across the series that the other ones we're going to compare to, note that we always have that benzylic position. Maybe we can always get some type of good reaction at that benzylic position. So let's go ahead and move one compound over and look at, one compound down and look at the energies there. This one that has the T-butyl group, you can see that the C3 position is still activated. It's styrenyl. That carbocation, when you remove the hydride, that carbocation can resonate all the way around the molecule, can delocalize, and you get a really stable species. The C6 position, similarly, pretty active, reasonably stable carbocation there. We can still have an opportunity over here to initiate a reaction sequence. That's still a pretty good number. That's still a tertiary carbocation. That's okay. If we did activate that position, it might be problematic in this exact substrate because you do have opportunities for carbocation rearrangement. You can make other tertiary carbocations through methyl shifts. So it might not be the best way to start, but it's still feasible. Oops, let's go to these two. Okay, so let's look at this pair and this pair. We're replacing the phenyl ring with a methyl group. And if we would have a methyl here, you still have allylic positions. At either of those two spots, you still have the benzylic position. We would expect this molecule to oxidize reasonably well. You can still rip a hydride off of the allylic position or the benzylic position. That's great. Look at the bottom molecule, similar story. We still have an allylic position here that's reasonable in energy, maybe a little bit higher energy, but maybe those two are still feasible. But that allylic CH bond can still get abstracted reasonably well. Things change when you go to the CF3. And the CF3 perturbs the energies associated with those carbocations pretty drastically. And so let's look at the numbers here for the top one. You put that CF3 there, you see the energy jump. Really tough to rip off that hydride. Think about the resonance structure there. What would the resonance structure look like? You push electrons over. That resonance structure would not be happy, right? Okay. We were talking about the destabilization of cationic intermediates, and with a different type of system, we were getting numbers like 10 to the 10 slower. Methyl versus CF3. And so in this molecule, we really don't want to rip off that hydride there, and we don't want to do this one either. Okay, the CF3 through the inductive effect is really destabilizing those cationic intermediates. And the same story is true over here. So over here, high energy, associated with formation of cationic intermediates for those two positions on the lower structure. Now the difference in reactivity in these two structures, this one is still reactive. It's 140, but it's still reactive. This one doesn't react at all. The difference in those structures is the benzylic position versus the T-butyl group. Okay, this one has a benzylic tertiary position. The reaction can still initiate by abstraction of the hydride at this C4 position to make a carbocation that's partially stabilized. In contrast, this position over here is deactivated. And look how far that CF3 group is. You're still several CC bonds away, right? 3 CC bonds away when you make that carbocation. But there's still a significant energy jump from the methyl to the CF3, and perturbing the reactivity several positions away. So those inductive effects can be pretty powerful. CF3 does not like cationic intermediates, right? Get used to that. It's going to be relevant as we move forward still. Okay, so now we're going to take this reaction, and I'm going to go back a couple. I said there are a couple of different mechanisms by which DDQ can act. A second mechanism is by H atom abstraction. So instead of taking off H minus, we take off H dot. If we take off H dot, we would be generating radicals at any of these positions. You can think about these two. You can also think about H4. I just didn't copy it in here. And the question is, how much of a perturbation do you get if you go through radical intermediates instead of cationic intermediates? Okay, so I'm going to give you just a couple of minutes to think about that. How big of a perturbation should it be if you're going through radical intermediates as opposed to cationic intermediates? Okay, and then I have another little set of animated slides to talk through those energies in just a couple minutes. Okay, so work on it. Okay, you had a minute to think about it? Are the effects going to be greater or less when you go through radical intermediates, neutral intermediates? We already said there's this huge effect when you go through cationic intermediates. Do you get, the basis of this question, do you get as big effect when you go through radicals? And so the answer, oops, I didn't copy that in. There we go. So here we're going to look at a slightly different series of model systems, and so it's like the lower line from before. Okay. And so you can see that we're just looking at the series that has the T-butyl group, because that was the one that was chemically resistant before. So let's look at the bond association energies. Again, calculated bond association energies. If we rip off H dot, you get a radical of that position. That's what we would be looking at here. And look at the perturbations there. 79 for a phenyl ring, 86, 84. Those perturbations aren't as drastic. The methyl to the CF3 are both reasonable numbers. CH bonds, 100-ish kcal per mole. Those are reasonably weak still. Let's look at the other position, 88, 88, 87. Minimal perturbation at all at that second allylic position. So what this is suggesting is that the radical intermediates are not substantially destabilized, whereas the cationic intermediates have these massive changes in stability. So you can do a lot more neutral chemistry with these. And it turns out that we did exploit this in some of our recent work. The conditions that we actually use to promote this reaction would be AIBN DDQ. AIBN NBS. So AIBN NBS. AIBN, an initiator of radical chemistry. NBS, a radical brominating reagent. Is this something that we've covered or going to cover soon? Next semester in synthesis? Okay, we're gonna tell them they have to go through this paper next semester so you can think a little bit more about what that is. The energy associated with succinimide, the stoichiometric product, the NH bond is about 93 kcal per mole, so strong enough that we can be ripping off these hydrogen atoms. Okay? But moral of the story is radical intermediates are destabilized less than the cationic intermediates. That's the key to think about here. Okay, we need to do a couple more real quick. I need to let you guys go for lunch in 20 minutes. So we're going to do this one, we're going to skip one, and then we'll do the last one. This one's going to be a little bit quicker. These are two prostacyclin derivatives. Prostaglandins, prostacyclins are important signaling molecules in the body. You should be studying those in your coursework, I would guess. We're just talking about the chemical stability in this case. Which one of those is going to be more stable? Look at the conditions. We're talking about acidic conditions, extra protons. Where are you going to protonate that molecule? And then how would that be perturbed? Okay. So let's go ahead and work on that for just a minute. Oh no, I messed it up. That's a different ring, huh? So I've already given you a hint on the chemical substructure we should be thinking about, but hopefully you're already thinking about that one because the fluorine atoms are already put in that position. Sorry? Oh, they should just be, that should be the ring, and then there should be the other.
That's the fluorine. That's what the fluorine.
So you've had a minute to think about it. If we put this molecule in acid, what's going to protonate? And I've already drawn the key functional group that we should be thinking about. Okay, and you're going to protonate the alkene. It's a special type of alkene. It's a vinyl ether. So the ether perturbs the oxygen, lone pair of electrons perturb the reactivity of that alkene. So we can draw those in. And the arrow push is going to be similar. It's a related arrow push if you think about ketone enol chemistry, or if you think about enamine chemistry. You'll see a lot of that in biological systems. You'll have, for example, you can protonate enols, and they'll react with some type of an electrophile by the same type of an arrow push. In this case, the electrophile is a proton, but you can have other electrophiles too. So that's going to be the type of intermediate we should be thinking about when we protonate the system and the electrons push down and we protonate the alpha position there. We would generate a cationic intermediate. Right? That's the structure that we've drawn right there. Now we should ask the question, how does fluorine perturb the stability of that intermediate? We've already talked about systems analogous to this. Remember we had the sugars, the nucleosides, that 5-membered ring, oxygen, and it was pushing off the nucleobase. We talked about that earlier today. And this is a similar structure. We pushed off we have a different mechanism by which we form this intermediate, but this is the same oxocarbenium ion intermediate. Okay. So we might think about forming the same intermediate in the other example. The other example would have a CF2 group. The CF2 group, those fluorine atoms are sigma withdrawing. The inductive effect is pulling electrons away. It's making delta plus character here at the difluorinated position. You also have delta plus character on the CsP2 carbon atom. And it's not good to have positive charge next to positive charge. Both of them are electronically disfavored, or having one next to the other is very disfavored. Okay. So plus charge next to each other, not favorable. We have an electron deficient species. We're trying to pull more electron density away from it, not favorable. So several ways of thinking about that, and I tried to explain it a couple of different ways so you can continue to think critically about this material. But that's not a good intermediate. B, it is more stable in acid, okay, because the intermediates are less stable. Fair? We can do one more. This one is going to be, it is in your notes. I will nudge you to think about it on your own, but the key feature is that this is also going to go through the same type of intermediate. Okay, the biological system is a little bit different. It's a carbohydrate. It's an antiviral agent. Okay, and there's some other things going on in the enzyme pocket that are activating the substrate, but you do have the potential, the capability now to think about this problem and arrive at what I hope is the right answer. Okay, and the references are down there a little bit later if you want to check those. They're really nice. You can look at the quality of those references, those citations. It's a nice paper. Okay, so the last one that we're going to do before lunch is right here. This is a recent FDA-approved drug. It's an eye drop. Look at that chemical structure. That does not look like any drug. And so, somebody approached me to ask me about like how this thing works and is it safe? And I was like, that can't be a drug. Like that, there's no way and it is. It's an eye drop. You put it on topically. Okay. And so the question for you all is, how is this thing going to work? And maybe I can just give you a little bit, a brief tidbit on eye pharmacology or physiology. Like I didn't know, I had to go look this stuff up. So this would be the eye, the outer layer, the cornea. You have a mucus, so there's a lot of glycoproteins in that, some other biological molecules, and then you come to this aqueous layer that has some other molecules floating around. It's aqueous, it's water, and we need that, or teardrops, right? We know our eyes are in general supposed to be hydrated. But in order to keep the water attached to the eye, you'll have like an outer membrane of an oily material. Okay, and that oil, like we need it because we need our eyes to stay hydrated, right? And so that's a lipid layer, and there's other things embedded in the lipid, but it's predominantly lipid on the outside to keep everything else moist down closer to the eye. Okay, how do you think this drug is going to work? We have a lipid and a fluorocarbon. What's going to happen there? Just think about it for a second. I thought this was one of the most clever things. It might be dangerous and toxic because you're like putting PFAS in your eye, right? But it's approved. They said it was safe enough. And I looked at some of the clinical data. It seemed like it wasn't building up in human tissue or rabbit tissue and some of the preclinical stuff. How does that thing work? I'm going to give you a minute or two to think about that. This is so cool. This is so easy. Have you seen this before, this molecule?
No, the molecule I don't know. Okay. But this is the CH and the CF. So this is the
Okay, so here's hint number one. What does the fluorocarbon interact with? What does it want to interact with? The water? The lipid? The glycoproteins? People are starting to think about that one because I didn't talk about that. Okay, what is the hydrocarbon trying to interact with? More hydrocarbon. That's interesting. Have you figured it out yet? So I gave you in your slides, you have this slide, you have another blank one just for continuing to take some other notes on it. We have to go back and think about this material here, right? We talked about this briefly, the way that the fluorocarbons don't like to interact with anything. And so you have the fluorocarbon tail and the lipid tail. And the way these are going to organize is going to, let me teach that or explain that. The lipid, the hydrocarbon, not necessarily going to be great in water, like low solubility between like a hydrocarbon and water. When you have other fatty acids, I said there's lipid, but there's other biological molecules in there. If you have fatty acids mixed in, the fatty acids can aggregate with a lipid tail, and then you have a polar anionic hydrogen bonding group down there to facilitate the interactions with water. So in these fatty acids, again, the reason why you have micelles and lipid bilayers and things like that in the body, this part, the anionic head, will interact with the water. The rest of the lipid will aggregate. Now you have this aggregation of lipid, and that allows the hydrocarbon to present upwards towards the air. Now with that organization, what happens? You have like Teflon on the outside of your eye. Does Teflon let water go through or out, like in or out? It doesn't. It blocks things from going in or out. It's kind of weird, okay? So think about the aggregation model here. And now let's extrapolate that to the setting that we were just talking about, the ocular setting. So here's another representation of what I kind of laid out for you here. Again, you have the cellular layer here. There's the cornea. The mucus layer, a lot of mucins and things there. Yes, you have biological molecules in some individuals that have like disruption to the nature of the lipids in the eye. You might not have a nice, smooth, consistent layer of the hydrocarbon across the outer part of the eye, and so you get some disruption there. When you use this as an eye drop, it helps reform the layer. You get the hydrocarbon inserting into the lipid layer there, helping rigidify and make a nice smooth surface, and then the perfluorocarbon stops water from evaporating. It keeps the teardrops in your eyes. It keeps your eyes hydrated so they don't get dry. Isn't that cool? Okay, so there's the secret. You kind of fill in the lipid layer in the teardrop, and then on the top you get like a Teflon that stops the evaporation of water out of the eye. I thought that was so cool when I saw it. All right, it was clever. So just some data. This is from the assay. You have like little wells. You put water in it, and then you just measure the evaporation rate. You do that by mass, right? It's a mass assay to see how quickly the water is evaporating. So this would be just the water in the presence of the perfluorooctane derivative. Perfluorohexyl, so it's a C6 with the perfluoro and then an octane after that. And so when you start adding in the drug, you see the evaporation rate slows. You have a couple of other assays here. This is with the mucin, so some of those glycoproteins that are in there. It works in the presence of some of those other glycoproteins. It also works in the presence of the mebum. That's the lipid layer. So you have to have the water underneath the lipid, and then you measure the evaporation. That's what this data is looking at. When you add the drug, you can see this synergy over here. So really cool system, I thought, explaining a lot of the basic principles that we were talking about, and it's a proof therapeutic. So hopefully you appreciate the interaction between the chemistry and the biology. Okay, so that's the final example I wanted to get through today. Hopefully it was useful, interesting, inspiring, and we have a couple of minutes for lunch now. Do we need any time for course announcements, or when are we getting started again, or what's the next step?
Thank you, Professor. I think it was a very interesting session. I hope you. दोनों भी? Okay, good afternoon to all. Yeah, so I hope you all had a good lunch, or all in a sleeping mode. Okay, so I think we already started with the very interesting talks today morning, and truly speaking, I am not a fluorine chemistry expert, but as a synthetic chemist, as a medicinal chemist, when we look at the data, when we look at the FDA approvals, and even sir in the morning, he mentioned that about 30% of FDA approved drugs, they have a fluorine in it. And it is not like it happened in last few years. It is like the first FDA approval was in 1954. And it is a very interesting chemistry. So as a synthetic chemist, I was always very fascinated. And when there was a GIAN course, so I approached Professor Altman, and I really wanted to learn, because I thought this is the only way like I can learn if I get chance to work with him, plan out complete course, and at least try to, because every day goes all busy in all other a lot of activities. So I thought, if I want to be, like, get into this chemistry, maybe then I should jump into like planning this course, so that it will be more of a learning experience. Okay, so that's why whatever tech talk I'm going to lecture today's lecture, I really wanted to understand what is the structural diversity of fluorinated compounds in the FDA approved drugs, because as a synthetic chemist, we always wanted to understand what type of different molecules are there, like which we have to actually synthesize. Okay, so if you in general, if you talk about in terms of pharmaceuticals in general, and there are small molecule drugs, there are biologics, and there are fluoropharmaceuticals. So among these, you know that organic small molecules, they have traditionally maintained a central position in the drug discovery, and they have really helped mankind in like fighting against various diseases. And you know, the small organic molecules, they are typically characterized by molecular weight less than 500, and because of their small size, they can easily penetrate cell membranes, reach to the desired target. Mostly it could be proteins or DNA targets, and their chemical structures are relatively simple. By simple, I again use the word relative, because I cannot say that they are very simple, but then the drug molecules which are there, like the medicines what we eat, like the chemists have worked so much like for so many years, that like they have really optimized the processes to make the chemistry look simple, even though it is complex, but they have chemists have really worked hard. So their molecules are, the chemistry is relatively simple. They can be synthesized from readily available starting materials, because the whole process tried to develop such that that these biologically active molecules can be synthesized easily. So the starting material also becomes automatically available. Okay, starting materials are natural products using established chemical reactions. But however, over the decade, the pharmaceutical industry has changed rapidly, and the change has totally, the focus of these pharmaceuticals has changed from small molecules to biologics. Like these are the biopharmaceutical products, and the biologics are currently the fastest growing class of pharmaceuticals, and have recently been among the highest selling drugs on the market. Okay, so now as a chemist, we need to understand that these pharmaceuticals are growing from a small molecules to biologics. And then if you see here the scenario, like this is a data of around 22 to 23 years data, and you can see that these are the small organic molecules, including oligonucleotides. Mostly the oligonucleotides are the molecules which are targeting DNAs or RNA, so that specific transcription can be altered, so that there is no like undesired proteins in the system. And you can see that there are very oligonucleotides are small in number, but you can see that like from 1998 few to it is growing, like almost there are few numbers are being getting approval. In terms of the total like only biologics, you can see that biologics slowly there was a steady number, but then now in last few years or last decade or so, you can see that biologics number is quite increasing. And like overall you can see around 25 to 30 drugs are being approved, and that number is also growing. And post COVID the number has increased drastically, like because like the whole mankind was in big trouble. Okay, so advantage of biologics is that they have high specificity and less frequent dosing, so that is advantage. Okay, so less frequent dosing is something that what I wanted you to remember. And the limitation of small molecule, why small molecules are now becoming less popular, or like biologics are, because they are highly specific. Small molecules are may not have specificity. Because of that there could be off target like toxicity issues. There could be resistance to like small molecules, and their short half-life. Okay, so that means the molecules, they get metabolized quickly, and because of their short half-life, that also becomes a limitation, and because of which the things are going to biologics. But now if you look at the fluoropharmaceuticals, the situation is little different. And interestingly, the situation is really different for fluoropharmaceuticals. In recent years, an estimated 20% of the marketed drugs have been fluoropharmaceuticals. And if you see, this is again around like 15 years data, and you can see these are new approved drugs. Okay, and then there are small molecules, and there are fluoropharmaceuticals. So you can see that fluoropharmaceuticals, the number is growing. Okay, and so that becomes very important to understand. And now if you see now another comparison, so like the fluoropharmaceuticals, like in 2015 there were like 10 fluoropharmaceuticals and 19 like other non-fluoropharmaceuticals approved, and that year the number of biologics were 12. Okay, in 16 the number was less. Okay, the overall approvals was less, but then if you just average out this 16 and 17, you will see that there is a steady increase in the number of FDA approvals. And you can see that like here around 34% of the total drugs are fluoropharmaceuticals, here 23%, here in 17 it is 25%, and the percentage of fluoropharmaceuticals is steadily increasing. Okay, so in 2019 around 43% of drugs, and in fact the number of fluoropharmaceuticals is now more than the biologics. So fluoropharmaceuticals, now it becomes clear that they are also as good as biologics, and because of some specific properties of these drugs, which are those properties are totally altered because of the presence of fluorine at specific position, so it really helps. So a recent story, this is very when I was just searching, I was preparing for this talk, you saw that the Gilead Pharmaceuticals in June 18, 2025, the Yes2Go, which is the Lenacapavir, is now the first and only FDA approved HIV prevention option offering 6 months of protection. So that means one single dose, and then patient don't have to take drug again for 6 months. Okay, so it is so that means you can see that this drug is so wonderful that only for a whole complete year you just need to dose it twice in a year. So what is so interesting about it? And now if you look at this drug, you will understand that why we are all talking about fluorine chemistry. So you'll see that a very like a complex drug, a big molecule, and you will see that there is a trifluoroethyl group present. There is a fluorine, like the methylene. Both the hydrogens are replaced by fluorine here. There is a trifluoromethyl group present. In the morning session, Professor Altman already gave several aspects of fluorine as well as trifluoromethyl groups on the on how to synthesize all those, how to look at the chemistry, and you can see there is a difluorobenzene. So total 10 number of fluorine molecules in one single molecule, and you can understand that it has drastically increased its metabolic stability. And now because when you take a small molecule drug like orally or in any way, it will be metabolized, and you know that if you have fever, we take maybe twice crocin twice in a day or thrice in a day maximum, and then next day fever is there, you will have to take that drug again, because drug will be metabolized, and the drug concentration in the body will not remain at the therapeutic window, because drug will be metabolized and that xenobiotic will be thrown out from the body. So there is a ADME, pharmacokinetics. So body will be starting working on it, and body will metabolize it, make it more water soluble, and body will try to remove it out. So now these metabolically soft spots are there in the drug. If they can be blocked by introducing a fluorine atom in it, the molecules will not be metabolized. But again, there could be a lot of pros and cons. If the molecule stays in the body for a long time, we also have to make sure that it is not toxic. But then this was a very interesting success story, because you know that for the lenacapavir is a capsid inhibitor, is used to treat adults with multi-drug resistance HIV-1 infection. It works by overstabilizing the capsid, which prevents the virus from releasing its contents inside the host cell. It interferes with the formation of a new virus particles, causing them to improperly shaped or less infectious. It prevents the HIV proviral DNA from being transported into the cell's nucleus. So again, you can see that the mechanism of action of this drug is it is overall actually trying to stabilize the capsid, and then the virus, the way virus infects, it gives out its nucleic acids into the host, so that it is preventing. Okay, and the major advantage of lenacapavir are its long-acting, twice yearly dosing and high efficacy of both HIV, for both HIV prevention, so pre-exposure prophylaxis and treatment. This reduces the burden of daily medication and significantly improve the adherence. So now you can imagine why I was telling about biologics. The advantage of biologics is that a very less frequent dosing is required, and they are highly specific. Specificity of the small molecules, you know, as a chemist, we can try to improve the specificity by altering the chemical structures. But then metabolic stability, if we can improve it, then definitely we can work on to modulating its pharmacokinetic properties, so that molecule is not metabolized, it remains in the system for longer time, and then the frequent dosing is not required. So what are these benefits of adding fluorine to drugs? So some of the components already Professor Altman has touched upon, but in my talk I just wanted to put several questions in your mind, so that the next 4 days expert is with us, and then we will be able to interacting with him, discussing with him on those questions. Okay, the fluorine atom possesses many intrinsic properties, and these properties include the atom size, electronegativity, and ability to block the metabolic oxidation sites, which I am calling it as a metabolic soft spots. Okay, so fluorine, if you see, like the small functional group allow molecule to fit in the active site pocket, but again in the morning we have seen that the size, like the H versus fluorine, there is a small difference, but then that difference is really not means with that difference molecule still can be accommodated into the active site pocket, and minor steric strain will result only minor steric strain, not very difficult to accommodate in the active site pocket. Its highest electronegativity leads to electrostatic interactions. Okay, so this is another advantage, that because of its electronegativity, so CF bond and so there will be a kind of a dipole, and that dipole, when it is present at the active site pocket, it is going to create a small like electrostatic interactions at the active site pocket. Now, and it also acts as a hydrogen bond acceptor. It is a very weak hydrogen bond acceptor. There is a slide we will discuss that its hydrogen bond capacity is not like a very usual hydrogen bond capacity. So, if there is a possibility of a actual hydrogen bond and a hydrogen bond involving like fluorine, so mostly the typical normal hydrogen bond formation will be preferred. So, the places where there is no hydrogen bond possibility, like for example, there is a greasy pocket, and if there is a fluorine present, that will create an advantage. So, I will give some examples to explain this. So, highest electronegativity also changes the overall dipole in the molecule, and then because of electronegativity, it lowers the overall pK of the molecule. Fluorine functional groups can raise or lower the lipophilicity of the molecule. So now, interestingly, it can actually either increase or decrease the lipophilicity depending on where the fluorine is present and how that dipole is total in the molecule. And fluorosubstituents deactivate ring from metabolic like oxidation. So so this is what actually the major advantage of having fluorine. But again, there are few cases where even aromatic fluorine was found to be like metabolized by the enzymatic metabolization, and it has led to formation of some like quinone kind of moieties, which I will give some examples as we go ahead. And the highest electronegativity also increases molecule stability. So you can see that they are color coded. So the blue ones and red ones, you can see that because of the presence of fluorine, it can change the activity. So pharmacodynamic effects, as well as electronegativity, it will change pKa, then it will change the lipophilicity. So because of fluorine, you can alter the pharmacokinetic properties of the molecule. And also fluorosubstituents deactivate ring from metabolic oxidation, so you can make the molecule quite stable. You can also increase the shelf life, as well as you can increase molecule metabolically more stable. So its excretion will be slow. So why fluorine modulate the physiochemical properties of organic compounds? So that becomes a question. And a few things we have already seen that so fluorine is a small atom with a high electronegativity and low polarizability. So even though it is high electronegativity, its polarizability is low. You can see here with its van der Waals radius 1.47 angstrom, fluorine occupies a smaller volume than typical organic substituents. So I am comparing fluorine now with the not H, but if you want to change those groups with the methyl, amino, or hydroxyl group, so they are like a little larger than fluorine. So we will be able to alter the molecule's properties by introducing fluorine instead of adding these other groups. The CF bond is strong and slightly longer than the CH bond. Compared to the CH bond, CF bond shows a reverse dipole moment. So Professor Altman also again touched upon this, and you will see that if you talk about CH versus CF, the dipole is completely changed. So what is the electronegativity of H and carbon? Remember from the 2 and 2.5. Okay, and now it is it changes to 4. So completely the dipole, you can see that the dipole is completely reverse because of the having fluorine. So shows the reverse dipole moment induced by the high electronegativity of fluorine. So these properties make fluorine a powerful modulator, okay, of the lipophilicity, the pK or electrostatic potential of an organic molecule. So we are going to see in detail how it is happening. Fluorine substituents can change the conformational preference of the organic molecules, and Dr. Altman is going to give very interesting discussion on these conformational effects of fluorine in his tomorrow's lectures. So fluorine can increase the metabolic stability of the drugs, which we are discussing a lot. Interestingly, as a synthetic chemist, we can see 19F, the only stable isotope of fluorine, has a nuclear spin of +½ and can thus be detected in an NMR spectroscopy, providing the alternative to more commonly used nuclei like other nuclei, which as an organic chemist we use it. So this becomes, so because of all these properties, fluorine becomes an important like atom to be introduced in the in the organic compounds. So fluorine lowers the pK of the compounds, and I think this is something will be very trivial for you to understand. The fluorine lowers the pK of the compounds primarily through a powerful inductive effect. As the most electronegative element, fluorine strongly pulls electron density away from neighboring atom. This stabilizes the conjugate base. So if you talk about some example these are very typical examples which we have learned in bachelor's, like acetic acid versus fluoroacetic acid, difluoroacetic acid versus trifluoroacetic acid, and you can see that there is a the tremendous decrease in the pKa. If you talk about ethanol versus 2,2,2-trifluoroethanol, you can see that the electronegativity has made the lowered the pKa like quite a bit. Phenol versus 4-fluorophenol, you will see that there is a lowering of the pKa, and now you can see that fluorine is at the 4th position. And as it is a strong, it is not a resonance effect, it is more of an inductive effect. As the atom is away, you will not see that pronounced effect, right? And then you can see that in the base piperidine, the pK of the conjugate acid is 11, whereas for 3-fluoropyridine, pK of conjugate acid, there are two interesting things, like it is 8.8 when there is axial fluorine at 3 position, whereas it is 6.6 for equatorial. So that means the fluorine is through space, also that the dipole is inducing the showing the effect of its dipole onto the acidity or basicity of the compound. So in general, you can see that in fluoroquinolones, fluorine increases the antibacterial potency and improves DNA gyrase complex binding. So the fluoroquinolones are the second generation organofluorine drugs after the steroidal glucocorticoids. In this autogipant, this trifluoromethyl as well as trifluorobenzyl groups significantly increase the drug's binding affinity to its target. So what I wanted to now show in next few slides about a diversity of the fluorine functional groups. You can see the fluorine is now here on the sp2 hybridized carbon, okay, and you can see maybe we can call it the whole together on a heterocyclic system. This is again fluorine CF on a sp2 hybridized carbon with not heterocyclic, okay, and then there are fluorine on the aliphatic carbon, and then this blockbuster drug Lipitor or atorvastatin, fluorine atom enhances biological activity and increases its resistance to metabolic oxidation here. So overall, pK values can be manipulated by altering the number of fluorine atoms, providing insight into drug activity as well as metabolic profile. So when we talk about hydrogen bond acceptor capacity, I said that fluorine is a weak hydrogen bond acceptor. And if you look at the data, this is from a recent paper, the number of hydrogen bonds found in a PDB repository, you'll see that the FHO hydrogen bond versus FNH hydrogen bond and versus FHC hydrogen bond, you can see that FHC is the huge number of very atypical hydrogen bonds, where this number is like 83%. So these are the examples where between fluorine on the aliphatic carbons and forming a hydrogen bond with OH, NH or CH. If you look at the another situation where fluorine is on the aromatic rings and the hydrogen bonding, you can see the scenario is very similar. So there is so fluorine was found to accept hydrogen bonds from OH, NH and CH, with CH being the most frequent donor. As expected, the interaction energy depend on the donor acceptor distance, because that is how they will form a hydrogen bond. However, it did not correlate with the FHX angle, which indicates that the hydrogen bond is not necessarily aligned with the lone pair of the fluorine acceptor. Also, the distances and the angles of the fluorine-hydrogen bond did not coincide with the energy minima of the corresponding isolated hydrogen bonds. This clearly tells that the enthalpy gain due to the fluorine-hydrogen bond, listen carefully, the enthalpy gain due to fluorine-hydrogen bond is likely not driving force for the binding affinity. So whenever there is a possibility of a typical hydrogen bond, that will be preferred over the C like FHC hydrogen bond. The fluorine hydrogen bonds probably form in addition to a stronger interaction that stabilize the ligand in the binding pocket. So this adds an extra edge, but then it does not drive the complete interaction with the receptor. So this is like a typical fluorine is a weak hydrogen bond acceptor, especially compared to oxygen and nitrogen. So this is a typical structure of fluorine in the hydrogen bond. So sorry, I think that it looks, so you can see that these are the hydrogen bond acceptor, and you can see the fluorine is at the extreme end here, where you can see the hydrogen bond acceptor strength of a fluorine compound is quite low, and whereas the other hydrogen bond acceptors like these other groups, they are very good like hydrogen bond acceptors, but not the fluorine compounds. So fluorine does not form a hydrogen bond with CH bond. Rather, a CH bond can act as a weak hydrogen bond donor. So Professor Bhartam will be giving some insights onto about how what are the aspects of how CF interacts with the receptor, so those aspects he will cover. Rather, a CH bond can act as a weak hydrogen bond donor to a more electronegative atom. The CH bond is not polar enough for this to happen very frequently or strongly. So CH bond polarity. So a CH bond is generally considered non-polar because the electronegativity difference between carbon and hydrogen is small. Therefore, it does not readily participate in hydrogen bonding as a donor. So when a molecule contains both CH and a fluorine atom, the fluorine can slightly polarize the CH bond, or this is because fluorine is highly electronegative and pulls electron density towards itself. So now, because of the presence of this like a very strong dipole near to the CH donor, it will induce the other neighboring CH to form a hydrogen bond. So the weak polarization makes the hydrogen in the CH bond slightly positive, delta positive, allowing it to act as a weak hydrogen bond donor to another electronegative atom like fluorine atom in a nearby molecule, resulting in that weak interaction which we are referring to as a hydrogen bond. So overall, while its high electronegativity means it has a partial negative charge, the lack of polarizability and the resulting short, strong bonds make it poor acceptor of hydrogen bonds from other donors. And that is why, like I was saying in last slide, that this fluorine as a hydrogen bond will not completely drive the interaction, but it will add an extra edge when the molecule is interacting with the receptor. So mostly as a medicinal chemist, I feel that, I think, correct me sir, if what I feel that, so whenever there is a fluorine atom in the molecule, mostly it should be the group should be fitting at maybe a greasy pocket. Like if there is more of a possibility of a hydrogen bond hydrogen bond donors, other like OH or NH are present, then that area may not be good to introduce fluorine over there. So that is what I feel that. So now it is quite different than a halogen bond. So in a halogen bond, so it is a Rx. Okay, so if there is when R is a carbon, okay, and X is like all the halogens. So when they comes close to another heteroatom, it forms an halogen bond, and the strength of a halogen bond generally follows the trend of increasing strength from fluorine to iodine. This is because as you move down the periodic table, the halogen gets larger and more polarizable, making them better at forming halogen bonds. So fluorine's high electronegativity and small size, however, mean it is the least likely to form a strong halogen bond. So if there is a bromine or chlorine in the molecules, they will prefer to form a halogen bond, which might add an extra interaction in your drug and receptor pocket. So how fluorine functional groups raise or lower the lipophilicity? Because one of the point which I mentioned on the slide, that fluorine can also have a dual role. It can increase as well as decrease the lipophilicity. So now increasing the lipophilicity is a common effect, especially for highly fluorinated groups. So whenever there is a fluorine groups, the fluorinated hydrocarbons, they increase the overall lipophilicity. Okay, so CF bonds like polar hydrophobic character, because it is now a polar bond, so also allows greater interaction with both polar and hydrophobic environments. So it is a hydrophobic, but because of the polar nature of the CF bond, it also adds now the hydrophilic little bit property to the molecules. So what factors increases the lipophilicity? So replacing hydrogen atoms with fluorine, which is generally considered more lipophilic than hydrogen, increases the overall hydrophobic surface area of a compound, and the perfluorinated chains, like mostly if there is a CF2, CF3 kind of hydrocarbon chain, this leads to some substantial increase in the lipophilicity of the molecule. The strong electron withdrawing nature of fluorine reduces the hydrogen bond acceptor capacity of functional groups like hydroxyl or amino on aromatic rings. So now if there is a because of the fluorine, these molecules OH and NH, they will not be act as a good donors, and that's why which increases the lipophilicity compared to the oxygenated analogs. Okay, so because these groups, their electron density is pulled by the fluorine via strong inductive effects. Okay, so these are the reason why the fluorinated molecules will become more lipophilic, but there are also a few factors where molecules may become decrease the lipophilicity. They will not become hydrophilic, but they will decrease the lipophilicity. The fluorine's high electronegativity creates a large dipole moment in the CF bond. This strongly pulls electron density away from the adjacent atom, increasing the molecule's overall polarity, and maybe a slight increase in the water solubility. So in aliphatic chains, the location of the fluorine matters greatly. So you will see that many drug molecules, the fluorine, the presence where they are present, that also matters a lot. So when there is an internal fluorination, placing a difluoro CF2 group inside a chain can sometimes decrease lipophilicity compared to the non-fluorinated version, due to a balancing of the hydrophobic surface with the strong inductive and dipole effects of the fluorine, whereas the terminal fluorination, placing a trifluoromethyl group at the end of the aliphatic chain, typically increases the lipophilicity. So again, these are the very relative terms. There is a marginal difference, but sometimes when it comes to a change in the pK properties, the presence of fluorine, their position, like in the aromatic ring also, whether they are present at the 4 position, at the 3 position, or in the aliphatic chain they are present at the terminal carbon or in the inside carbon, it slightly changes the lipophilicity of the molecule. Okay, so fluorine containing drugs approved by, so now because of all of this very interesting aspects of fluorine, no doubt, I was saying that the number of FDA approval drugs with fluorine is increasing. So now if you see that, this is a paper published in 2023, where data was up to 2019, and you can see that first fluorine containing drug was introduced in 1954, and for that decade the number was 17. The next decade the number of fluorinated compounds was 11. So now after about 3 decades, you can see the number has doubled, increasing, if not double, but from here. And then from 1980 to 89, it is again 10 more drugs extra, from 20 to 32. From 1990 to 99, the number has changed from 30 to 60, it remains same. And then from in another decade, 2010 to 2019, the number of fluorinated compounds has increased to 79. And now if you see the year-wise, this is the data published, and now this is the data what we compiled. In 2020 to 2025, this is yearly data, you can see that the fluorine containing drugs, so every year now the number of drugs have increased. So 2020 is 13, then 9, so in 22 it is dropped, but then if you just average out these two together, it is like around 10. So you can see that like since 2020, almost 10 drugs are being approved by FDA, which are fluorinated. So like from 1 to 2 to 3 drugs, or to 5 to 6 drugs, or 8 drugs in a decade, it has changed to about approximately 10 drugs per year since 2020. So really fluorine compounds. So this is the first example. The first fluoropharmaceutical was this is Fluorinef, or Fluorinef acetate, which was brought to market in 1954 by BMS. So Fluorinef, and you can see that the fluorine present at the C9 alpha position of a steroid. It exhibits potent mineralocorticoid properties and high glucocorticoid activity. The next, maybe a series of drugs was fluoroquinolones. These are the new generation of quinolones, such as ciprofloxacin and norfloxacin and levofloxacin. They were introduced in 1980s and present a second historically significant group of fluoropharmaceuticals. Fluoroquinolones act as a potent antibacterial agents by inhibiting the activity of DNA gyrase and topoisomerase, quite different than the usual antibiotic which were there, like sulfur drugs or penicillins. So this was a complete new generation of drugs, and the fluorine like drastically improved its metabolic stability. The another drug, Lipitor, I purposely added this because we all are chemists here. In 1985, a chemist, Warner Lambert, named Bruce Roth, a chemist at Warner Lambert named Bruce Roth, first synthesized the active ingredient, atorvastatin. In 1996, after securing FDA approval, Warner Lambert entered into a co-marketing deal with Pfizer to sell this drug. In 1997, this drug Lipitor was officially introduced to the market, and in 2000, Pfizer acquired this Warner Lambert in a landmark deal of $90 billion deal, and this is really a blockbuster drug since then. So I think we all should be proud as a chemist that a fluorinated or any synthetic small molecules can be of such a value. Okay, and then now and it's a fluorine containing drug. This blockbuster drug, atorvastatin, sold under the brand name Lipitor, among others, is a starting medication used to prevent cardiovascular diseases, has a fluorine in it. So looking at this so far, the diversity of fluorofunctionalized fragments in fluoropharmaceuticals, so you can see that there is a majority of the compounds, there is a fluorine is present on the sp2 hybridized carbon, or CF3 is present on the carbon. CF3 is also present on the heterocyclic structures. Fluorine is also present in the form of chiral centers. Then there is SCF3 groups are present, OCF3 groups are present. So the diversity of the fluorine containing compounds is enormous. This is the data up to 2019. Since then, there were around 64 more molecules were FDA approved, and the number is over 400. And you can see that this is nicely ssummarized in this review, ACS omega. So where you can see that among these 369 molecules, 167 are those where fluorine is attached to a sp2 hybridized carbon. The reason I am trying to describe this to a medicinal chemist, because we need to understand that the importance of the groups like Professor Altman's group, who are actually developing methodologies new methodologies to introduce fluorine in different functional groups, in different scaffolds. And you can see that majority of the drugs, they are 167 are on the where fluorine is attached to sp2 hybridized carbon. Then comes 55 drugs where the fluorine is attached to sp3 hybridized carbons, means they are in the aliphatic chains. Next is where CF3 is attached to an aromatic groups, followed by a fluorine attached to a sp2 hybridized carbon, but it is a heterocyclic moiety, the number is less, followed by a CF3 attached to a CF3 attached to a heterocyclic moiety. This is a fluorine attached to a heterocyclic moiety. Then, like you can see that there is a methylene in the drug. Like it is not at the terminal position, but at the internal position. The difluoro methylenes are the very frequently found functional groups, followed by then OCF3s with aryl ethers. Then there is a CF3 in the alkyl group, so it's the terminal chains we have seen in few of these drugs, followed by we can see that there is a CH2F. So the terminal like methyl, only one of the hydrogen is replaced by fluorine, or you can have a in the this group is very frequently found trifluoroethyl with nitrogen or oxygen. These are also few drugs have these groups. Then comes you have a trifluoro groups, CF3 group on aryl ether, followed by CF3. So this is the one which I was just telling, trifluoroethyl on attached to nitrogen or oxygen, and so on. So now like you can see that the few other groups are quite less in number. So if you see, now I just wanted to show that very interesting among this database, the number of drugs with fluorofunctionalized heterocyclic fragments was relatively low. So you can see that where the fluoride is attached to a heterocyclic group, the number is less compared to they are attached to a non-heterocyclic rings. And the structural diversity was also highly limited. Among these 42 drugs, the total number of fluorofunctionalized heterocyclic fragments was 43. So that means if there are among so there are 6-membered ring with one nitrogen. So 8 drugs had only fluorine, then 6 drugs had CF3. In 6-membered ring with the 2 nitrogens, there were 12 compounds with fluorine, 2 with CF3, 1 with CFH2, 1 with CF3. And if we talk about another heterocyclic drugs where you have a nitrogen or oxygen and the fluorine is attached to an sp3 hybridized carbon, you can see in 6 members there were 4 drugs and in 5 members there were 9 drugs. So overall, the overall looks like that the fluorine present on the sp2 hybridized carbon in a non-heterocyclic moieties are very frequently present, and the reason is that maybe those groups are very easily getting metabolized, and the metabolic hotspots are mostly on those aromatic non-heterocyclic aromatic structures. Okay, so this is that drug which among these two, so you can see that this is a drug where the fluorinated groups are with 2 different functional groups, here it is in the pyrimidine scaffold and here on a different scaffold. So that's why this among these 42 drugs the number became 43 because of this exception. So overall, just wanted to summarize all these structures together. So you can see that a few examples, I'm just trying to show you the structural diversity. You can see fluorine on the sp2 hybridized benzene ring, and then you have the CF3, okay, the trifluoroethyl group. Then we have interestingly another group where on a tertiary butyl group here, one of the methyl is changed to CF3. Then again a similar group which we have just discussed. We have now CF3 on the pyridine scaffold. So as a chemist, we will have to see that we have this diverse toolbox to develop methodologies to introduce these drugs. And in this course, we will be talking about some chemistry aspects also, where we'll talk about various different reagent for fluorination. Okay, so again, you can see that there is a trifluorobenzene. Then there are also 18 fluorine 18 isotopes are also introduced here. Then you can see difluorobenzene. You can see again a similar group where you have a tertiary butyl group. One of the methyl is changed to CF3. You have So you can see that then you also have fluorine in the chiral moiety. So it is on the sp3 hybridized carbon, but in the you have a stereo center. So that means as a chemist you really need a diverse chemistry understanding to build this molecule. Like not only in the 2D structures, but also we need to look into how we should have methods to synthesize chiral fluorinated compounds. If you see now the heterocycles, you can see a diversity. You can see that naphthalene, you can see the fluorine is present in the nucleobase, like this is imidazopyrimidines. Then we have fluorines in the benzene. Then we have pyrimidine, like 2 ones. We have like fluorine in the pyrazine. So you can see that whatever all different kinds of function like heterocycles are present, where fluorine is present, and mostly in many of these molecules they try to block the metabolic hotspot, or also sometimes they increase the activity because of the electrostatic interactions or a weak hydrogen bond capacities. Okay, so just wanted to tell that it is not maybe we can call these as a privileged structures, because they are present in molecules which are for different like applications. So again, for sp2 hybridized carbon heterocyclic F, so you can see that there is a variety of molecules where fluorine is present. In the another set, you have a sp2 hybridized and a heterocycle where one fluorine is present, and you can see that starting from antivirals to anti-cancer activity, or some anti-diabetic activity. So the molecules, the fluorinated compounds are kind of, we can say, privileged structures. Okay, so now fluorine is also present in the molecules which has a chiral center. And there is a very interesting thing, that thalidomide story. So the thalidomide story. The racemic thalidomide was launched in the 1950s in Germany and a few other like first world countries as a sedative hypnotic and as a medication to treat morning sickness. So however, unexpected teratogenic congenital disabilities were reported for babies delivered from moms who took thalidomide during their pregnancy, delivered from mothers who took the thalidomide during their pregnancy, which led to a withdrawal of this drug from the market. So this story, I think as a medicinal chemist you might have heard. So later the S enantiomer of the thalidomide was found to be teratogenic, and like R enantiomer was actually was the most active form, but then you cannot actually just make the R enantiomer and give, because it will get racemized, okay, in the biological system. So interestingly, despite its devastating side effects on unborn children, the racemic mixture of thalidomide is now back on the market as an effective drug for treatment of leprosy and multiple myeloma. Given the enhanced metabolic stability of the carbon-fluorine bond, use of chiral fluorinated thalidomide is being explored as a potential strategy to overcome the unavoidable. This is not the drug in the market, but then people are exploring this introduction of the fluorine will avoid the racemization. Okay, so the S fluorinated thalidomide showed to be a 2 times more potent than R enantiomer in its anti-tumor activity. Okay, so with this scenario, I'm just telling that the fluorinated compounds are good, but then again there is a dark side of the fluorine. So as a medicinal chemist, as a thinking chemist, as a clever chemist, we also should know what are the possible dark side of the fluorine. So we just discussed so much that the fluorine can be because CF bond dissociation energy is high, and fluorine is often used by medicinal chemists to block the metabolic soft spot. So there was a review again recently published. So many times there is a CF bond can be cleaved due to chemical instability or metabolism, and leaving fluoride ions or the toxic metabolites may form as a result. And Professor Altman also in his talk mentioned about one example. So despite the perceived stability of CF bond, chemical instability and drug metabolizing enzymes can lead to its cleavage. The resulting release of fluoride and formation of a certain metabolites may cause safety issues and warrant a medicinal chemist's attention, and that's why it is very important to understand what all different chemistries can happen. Few examples I have just added here from a recent review. So you can see that the SN2 reaction involving monofluorinated alkyls. So in this group you can see that this moiety was subjected to a solution stability test. This was a study done at Pfizer. At the physiological pH at 50 degrees Celsius, there was a displacement of a fluorine to form this aziridine, and then which opens up to get either 5-membered or the 6-membered structure. So fluoride ion is coming out, and also there is a the change in the structure. So they could be these molecules, if this happens in a drug, it could be toxic, or it may have some different activity. If you see the fluoroleucine in vivo, if it is present at the terminal carbon, it can get cyclized to form lactones and leaving the fluoride into the system. You can see if there is a fluoroalkyl moieties in the group, this glutathiones, cysteine SH, can react with this and to form conjugates and may lead to undesired activities. If there is a lone pair of electrons or delta negative center at fluorine's beta or other homologous position, that also lead to instability to the molecules. And you can see that here, when the electronegative or the lone pair or delta negative part is at the beta position, and you can see that, for example, in compound 8, the lone pairs can push the fluorine out, form an imine ship base, which then will react with water to form the respective keto derivatives, and this can be avoided by introducing an amide bond. It can be reduced, but so if a chemist understand this point of possible metabolic instability, we can alter the molecule. But again, if you alter the molecules activity may change. So, but then we'll have to keep that also in mind while we are altering the molecules. The another possibility here, you can see that when there is a fluorine on the alkyl chains, okay, so this is a difluoromethyl group on a imidazole at 1, 2, 3, at 5 position, you can see at pH 7.4 at close to room temperature, it can push out the fluorine, forming a reactive intermediate which can react with water to form a formyl group, and which again then leads to a so this is like a oxidation, and similar metabolic oxidation can happen in the body. Similar reaction is also shown on this substrate, indole-based substrate. So you can see that some of these molecules, they are not drug molecules, but then some of the active molecules during the drug discrete process, they are exposed to human liver microsomes. So you can see that here O demethylation. So this will result into O demethylation, and after O demethylation, you have the OH free, which will push out the fluorine to get so fluoride ion will go out, as well as it will form another moieties which may result into toxic effects. In another moiety, it can also lead to N-dealkylation. So because if the cytochrome P450 or cytochromes may oxidize this molecule to form an OH here, resulting into hemiaminal, and which on dealkylation, you can imagine that it will form, this bond will break here, CN bond will break to form a formyl group, and there is a fluorine present which will eliminate to form the Michael acceptors in the body. And now once you have Michael acceptors, so similarly this is another case where human liver microsomes will result into amine or alcohol oxidation, resulting in an imine, and then there is an elimination, so it will form an Michael acceptors. So such Michael acceptors in the physiological system can lead to conjugation with the glutathiones or any other proteins in the body, and can lead to side effects. So now you can see that if you replace this hydrogen with methyl, such metabolic oxidation can be avoided. So chemists should know that maybe we'll have to develop methods, or we should try to see that that we introduce a methyl here, and then the molecule formed may be metabolically more stable. Okay, so another few examples, just 2 more slides, and then I will break. So you can see that there is an oxidation of alkyl fluorides. So here the CIF mediated hydroxylation will result into hydroxy compound, which will then get to a keto form, or then there will be a or you can see that the similar hydroxylation will result into formation of COH, and then it will push out the this formyl fluoride. Okay, will go out, resulting into an OH phenol, which will then get oxidized to quinones kind of compounds, which are which are more toxic in the biological system. Similar oxidative defluorination of aryl fluorides is also reported, where these fluorides will get oxidized, and then there will be hydroxylation to result into quinones or quinoneamines or quinone methides. And these molecules, they are they get into many conjugation reactions or side reactions to show some undesired side effects. Another group, like this is the oxidation of an alkenyl fluoride. This is mostly used as a bioisoster of an amide, and it can actually go epoxidation and followed by cyclization to lead to a fluoride elimination from these molecules, also resulting into another metabolites, which may lose the activity or may result into toxic effects. So dealkylation may lead to toxic metabolite formation. Okay, so here you can see that here because of the N dealkylation, so this is a acetaldehyde, fluoroacetaldehyde will form, which will then oxidize to fluoroacetic acid, and then it can again react with the other biomolecules to form toxic side products. So similar reactions can happen here in this kind of moieties also. So oxidative defluorination. So like that, there are many reports of where fluorine compounds are getting oxidized, metabolized, and then there are possibilities of generating some side effects. So even though the fluorine compounds or organofluorine compounds are very important, as a chemist, it is very important to also understand what are the metabolic soft spots in the drug, and how we can develop new chemistry also to take care of these challenges. So with this, I will stop here, and we can take some questions. Yeah, anything? So overall, it was the idea to just showcase like what all diversity is present in the FDA approved drugs, so that you will have a lot of questions in the mind about. And then when Professor Altman was taking you through some questions, when you are pushing the arrows, you will be able to understand how these molecules can also lead to different reactions. Even though the CF bond is so strong, but even a few metabolic degradation is very well reported. Yes? So no questions? Okay, then I think we will take a break, and we will take a maybe 15 minutes break, and then we will gather back to listen to different chemistry aspects of different fluorine chemistry. Okay, where Dr. Madhuri will take you through different reagents for fluorination. Okay.
So, good afternoon, everyone. Today's session, I think it is really a brainstorming session because as soon as this GIAN course started, everybody was in, I think you might be on Google, that what is this fluorine chemistry, how many drug molecules are there, how many percentage drugs are having fluorine, and then everyone feels like, okay, I will also have some fluorine molecule, I will synthesize it, I will get good paper. And once you come here, then Professor Altman, he mentioned that what you are feeling, that it is a isoster of hydrogen, that's not true, and it has little bit different properties, different size. Then Dr. Deepak, he showed you so many drug molecules, and at the end, when like it was very promising picture and we think that okay, we'll also have such kind of molecule, he mentioned that how it gets metabolite and it might have some adverse effect. Okay, so what now we learn from all of this is whatever we are going to plan, we have to plan it wisely. And obviously all of we know that whenever it will go in market, there is a long process. So anyway, that will be taken care. But since if you want to introduce fluorine, how we can how we can introduce it, or what are the reagents we have, so that we are going to discuss now. Okay, so I will skip this slide because you already know there are so many drug molecules and they have variety of fluorine atoms. So, and one more thing, I would like to thank Professor Altman because when I was preparing on this topic, he very kindly shared his material with me. So for me, it became very easy to prepare this talk. So for introduction of fluorine, there are two ways or two methods. You can see here A and B. So A is called as a traditional way, in which what we do, we take starting material which already has fluorine atom, and then we club it with other molecule and do little bit modification, and then our molecule is ready. But this approach is not very feasible because suppose you want to do SAR or you want to introduce fluorine at many places, then you need different starting materials, right? So every time you have to find out molecule which has fluorine and that component you have to club. So that is not very feasible. So another approach which is called as advanced method. In this advanced method, what we can do, that we have our desired pharmacophore, or since you are students which are interested in drug discovery, so you have molecule and then somehow you can replace this CH with fluorine. So you have many reagents which directly replace this hydrogen with fluorine, and that we are going to see. Another way is you convert this H into some other functional group, right, like halides or OH, and then you do fluorination. Okay, so for this path A, you need some reagent which is the source of F minus, so nucleophilic fluorinating reagents. Another way is you can have some carbon metal bond and then you can use some electrophilic reagent which is a source of F plus, and then you can introduce fluorine by that electrophilic reagent. So basically these are the two types, nucleophilic and electrophilic fluorinating reagents. In nucleophilic fluorinating reagents, again you have alkali metal fluorides, tetraalkyl ammonium fluorides, and there is one different class which is called as a deoxygenating fluorinating reagent like DAST. Okay, so where you will replace OH directly with fluorine. Now in this talk I will not cover the reagents which will be used to get CF3 or CHF2 or CF2H in your molecule. So basically most of the reagents are for the introduction of single fluorine atom. So you have these electrophilic reagents. Okay, you can see here these are electrophilic reagent, and if you observe this structure, basically they have nitrogen fluorine bond. Okay, and you have another class of compounds which are nucleophilic reagent, in which there is a sulfur fluorine bond or carbon fluorine bond. So whenever we are going to use reagent in our day-to-day practice to get fluorine in our molecule, what we will see for process chemistry, people they think more about yield, cost of the reagent, and impurity profile of product. Okay, means if it is giving you some other byproducts or something like that. In medicinal chemistry, it is more about availability of your starting material and can you do it, introduce fluorine in later stage, okay, so that there is no much problem. So these things we have to keep in our mind, and accordingly we have to use reagents. There are, I will show you n number of reagents are there to introduce fluorine, okay. And why this is so, like Dr. Deepak mentioned you that in last decade there is a huge increase in number of drug molecules which has fluorine. So there was continuous pressure on organic chemists that you have some methods which will be easy to introduce fluorine. So from that point of view, many methods have developed which introduce fluorine in organic molecule in simpler way. Okay. So first I will talk about fluorination of compounds which are aromatic in nature, okay, and these are pre-functionalized aromatic compounds. In this compound you can convert aromatic amine to corresponding diazo compound, and initially this Ball-Schimann reaction, this was used for this purpose, and this diazo compound was isolated, and then by nucleophilic displacement we can get aryl fluoride. Okay, so you can see there are so many compounds where fluorine has introduced. Now, this Bookwood and co-workers, they developed new method in which there is no need to isolate these diazo compound. Okay, so they have not isolated it immediately. They have done fluorination, and it has enhanced the yield of this reaction. Okay, so this is a very good modification they have done in this reaction to get fluorine on aromatic carbon or sp2 carbon. Okay, the halogen exchange reaction is another example in which again you can get fluorine on sp2 carbon of your aromatic ring. So for this purpose, this tributyl ammonium fluoride, it was generated in situ by reaction with tributyl ammonium cyanide with reaction of, by reacting it with hexafluorobenzene. Okay, so you can get this compound in situ, TBAF, and that you can use for fluorination. So this reaction again it gave excellent yield, and you can do that reaction in room temperature. Okay, so that is again very good method. So one more method to get fluorine on sp2 carbon or fluorine on aromatic ring is by replacing OH group like phenolic group by fluorine. Okay, so this can be done by phenofluor. So name itself suggests that phenol is getting converted into fluorine. Okay, so for that purpose you have this 2,2-difluoro-1,3-diaryl imidazoline ring. Okay, so this kind of compound you have which you can use for fluorination, and again this reaction is used to displace OH on aromatic ring to get fluorine there. You can, if you do fluorination in case of electron-rich aromatic system, heteroaromatic system, usually you get fluorine at third position. Okay, if you want to get fluorine at second position, then what to do? So you can use this carboxylate, okay, at second position, and then you can easily introduce fluorine at that second position. Okay, so this is another method. So far we have discussed the few methods by which you can introduce fluorine on sp2 carbon of aromatic ring. There are huge number of reagents which use transition metal catalysts to do this reaction, but I will not talk about that. Dr. Ravi will talk about that topic maybe tomorrow or day after tomorrow. So now we will shift towards fluorination on aliphatic substrate. How we can get fluorine on aliphatic substance. So we can do that by using alkyl halide or alkyl triplet, means you have some good leaving group, right? And then you can use nucleophilic reagent which will displace that leaving group, and you can get fluorine. Okay, but problem with that, whatever nucleophilic reagents I have mentioned in earlier slide, those are either metal fluorides, so solubility issue is there. So cesium fluoride is better soluble. Again, if you want to use KF, potassium fluoride, then you have to use phase transfer catalyst. Okay, or then you can use this TBAF, tetra-alkyl or tetrabutyl ammonium fluorides. That will increase the solubility. Those are soluble in organic solvents, and you can use such reagents. Or you can use compounds like tri-tertiary butanol amine. These compounds can be used as organic promoter, and it will help to increase the yield of your fluorinated compound by eliminating, by reducing the amount of elimination product, right? Because you have learned that whenever you want to introduce fluorine, sometime you get double bond there. That gets HF gets eliminated and there is a double bond. So that can be reduced by using such kind of promoter. So this is one method in which you can introduce fluorine on aliphatic substrate. Another method, you can use such kind of catalyst, and you can again use that catalyst along with KF, and you can do nucleophilic displacement. You can displace OTF, O triplet, and you can get fluorine there. So these are the methods for introduction of this fluorine by displacing it triplet or some halides, okay, bromide or iodide. You can use one more reagent which is called as a dust, and I think everybody knows dust because this is somehow very famous reagent of chemist. Okay, actually this reagent has few problems. What is the problem? It undergoes non-energetic disproportionation, so it will form this SF4 sulfur tetrafluoride and this bis ethyl amino sulfur difluoride. Okay, this further it will degrade and it is explosive in nature. So handling of this reagent, there is a little bit problem, but still it is a very good reagent because it gives very good yield. Okay, so you can use dust. And how it works? So if you have alcohol, that OH will be replaced with fluorine, and most of the times you get inversion in configuration, but there are reports where you have retention of configuration, or in some cases there is a rearrangement. Okay, so you have to remember that also. So initially this OH, it will attack on this sulfur, right? Sulfur of this dust, and F minus will go out. Then lone pair of nitrogen, it will form sulfur nitrogen double bond. Again F minus will go, and that F minus will attack from backside, and so that you will get SN2 kind of reaction with inversion. Okay, so you will get fluorine with inversion. Whatever OH was there, exactly opposite stereochemistry will be there for fluorine. Okay, so there is another method in which, sorry, okay, where this fluorination is done of this aliphatic OH. Okay, so here also they have used dust, and what you observe that you get inversion in configuration as a major product. So 31% you got this compound, but you will also get a compound with retention in configuration, and there is also rearrangement product. Now why it is so? Because there is a formation of this transient aziridium ion. Okay, so this will form. So whether it is your medicinal chemistry or organic chemistry, you have to always look up around your reactive site, that how it is going to alter your wave. Okay, you are desiring something, and if you are not getting, you have to see, or initially only you have to say that okay, here it is there, so it might affect the stereochemistry. Okay, so you will see that even though inversion chemistry, inversion compound you have major, you are getting another two compounds as well. And sometimes people don't mind if you get such kind of other compounds. It is good, you can have diverse library of molecules. Okay, so you can use that library. So that's what it is done for this case. Okay, so this fellow has done so many fluorination reaction on different slightly different starting materials and got different compounds. Okay, so that is a library kind of thing. Now dust also used to get fluorine in 7-member ring. Okay, so in azipanes also you can get fluorine instead of OH. But now if you see here stereochemistry, you are getting here fluorine with retention of configuration. Now it is because of this Bock group which is acting in neighboring group participation way. Okay, and that's why there is a double inversion, and that's why you are getting retention here. Okay, now similar system you have in this compound also, but now your compound is having double bond. Okay, so since it is having double bond, now that neighboring group participation, it is not that much feasible, because you will have that fused system, and in fused system it is 5 fused 4 kind of thing, and then it becomes a little bit rigid system. Okay, so you can't have double bond. So neighboring group participation is not much, and that's why you are getting, even though this Bock and OH are like 1 carbon away from each other in both the cases. Here also you have 1 carbon, here also you have 1 carbon. But here dust is giving you compound with retention in configuration, and here it is giving you compound with inversion in configuration. Okay, so this is because of here neighboring group participation of Bock is there. In this case it is not possible. Okay, Now again, this is very important. Whenever you have fluorine and in consecutive ways, it will affect conformation. So this is an example of synthesis of alpha, beta, gamma, trifluoro, delta amino acids. So you have these 3 fluorine atoms, right? And if these are all syn, then it will have bent kind of geometry, okay? And if you have syn anti, then there will be zigzag geometry. Conformation will be different. Now how to get these two compounds? So initially if you treat this compound with deoxofluor, actually what you have to do, this somehow you have to remember names, because I am going to use these reagents again and again, okay? So you have to remember those names, and then it will make sense to you, okay? So we have to use deoxofluor. It will again do displacement reaction, and we are getting here fluorine. Again, it is a dust kind of similar class of reagent. So you will get inversion of configuration. Now, as I mentioned in the beginning itself, that dust, even though most of the times you observe retention in configuration, sometimes you get inversion in configuration, sometimes you get retention in configuration, okay? Now here carbocation formation is prevented due to presence of this nitro group, right? Because it will not stabilize that carbocation at benzylic position. So that's why you are getting only SN2 product. Again, this TMS morphylin, it will stabilize, it will prevent SN1 path. So that's why you are getting fluorine with inversion in configuration. Now for this epoxide opening, you have to do a little bit strong condition, microwave irradiation you have to do with triethylamine and TH and hydrogen fluoride. So you will get this compound, okay? Again, this fluorine attacks at this position or that position, that doesn't matter, because anyway your final product in that two will be same, okay? It is going to, here also if it attacks, as I shown you, it is at by beta way. If it attacks at this position, again here also it will be beta. And then you are again using deoxofluor, so inversion in configuration, and you are, whatever this alpha OH, that will be replaced by beta fluorine, okay? So you are getting here anti-syn conformation of 3 fluorine atoms. If you want all syn, then first you have to do Mitsunobu reaction. You have to invert that OH and again follow same sequence. You will get all syn 3 fluorine compound, okay? So that's how you have to do these reactions. Now synthesis of dipeptyl peptidase, okay? This is a very good inhibitor for the type 2 diabetes, and in this it has shown that how DAST is used to introduce fluorine. Okay, so 1.1 to 1.2 equivalent of DAST at minus 78 degrees Celsius, you can get 70% of yield of this compound, and further on transformation you can get your desired this peptidase compound. Okay, now another class of compound, that is fluoroamino reagent, which is also called as a FAR. Okay, so in this you have this fluoro and dialkyl amine group, and this kind of reagent are used for the displacement of OH, and at the place of OH you will get fluorine. Okay, so these are the reagents which you can use in your synthesis. So here you can see that deoxyfluorination using this FAR reagent, you can convert epoxide to corresponding difluoro compound, or you can convert 1,2-diol to fluoro compound. Okay, fluoro, and you have here ester group, which later you can hydrolyze, and you can use one more reagent and you can introduce fluorine here also. Now extal fluor, again this is one more reagent, and it is also used to introduce fluorine, and you can displace this OH and you can have fluorine with inversion of configuration. Okay, so this is a dialkyl amino difluorosulfinium tetrafluoroborate salt. Okay, so this is a salt, and since it is a salt, it is a crystalline bench stable compound. Otherwise, you know that dust, it is difficult. Initially I told you that it will undergo disintegration and it is explosive. So handling becomes a little bit difficult, but you can use, now such a reagents are there, so you can use these reagents and it will do same work for you, like it will replace OH with fluorine. So you have this reagent as well. Now here if you use external source of fluoride, that F minus from external source you will attack here in SN2 fashion, and you will get fluorine. If you are not using that external fluoride source, and if you are using base, then this base will promote hydrogen here. It will form sulfur nitrogen bond, and then F minus will be ejected, and that fluoride ion will attack here, and you will get fluorine with inversion in configuration. Okay, so these we are just seeing different reagent. Like few reagents, there is some problem with solubility, stability, and then you have advanced reagent. Like with initially we talked about KF, you have to use phase transfer catalyst. Okay, so instead of that, you use some tetrabutyl ammonium fluoride. Okay, so instead of that, again that will solve problem of solubility. Okay, so like that you have different reagent. So you will do something, you will face problem, and then there is another reagent. So you should know about all these reagents. Okay, now flow lead, again this is a new reagent and it is a refined version of phenyl sulfur trifluoride. Okay, so this is your reagent which is called as a flow lead. It will also do introduce fluorine, and instead of OH you can have now fluorine. Okay, so flow lead is easily accessible in high yield, and you can prepare it or you can get by reaction with zinc chloride with 3,5-dimethyl tertiary butyl benzene with S2Cl2. Okay, so if you treat this compound, you will get this, and you can use that reagent to get fluorine in your molecule. So it is a shelf stable and it is easy to handle crystalline solid. Okay, so it has advantage over dust. Phenofluor. So we have discussed earlier that phenofluor, it is generally used for displacement of phenolic OH group, and you can get fluorine there. But you can also displace OH in aliphatic substrate and you can get fluorine there. Okay, so this is a phenofluor reagent. Again, it has structure like this. We have initially seen the structure. Okay, so this lone pair of nitrogen here, it will attack, it will form carbon nitrogen bond, F minus will come out, then OH will attack here. Okay, so you will get this kind of intermediate, then base will abstract this proton, and again this lone pair of nitrogen, it will come in picture. There is a formation of carbon nitrogen double bond, F minus will get eliminated, which will attack by SN2 fashion, and you will have now alkyl fluoride. Okay, so this you can use for displacement of aromatic OH. It can be used for the displacement of aliphatic OH as well. Now phenofluor is very good. You can see that there are 1, 2, 3, 4, 5 hydroxyl groups, but selectively it will fluorinate only this OH, which is in red color. Okay, because this is a tertiary OH group, and rest of the OH are forming hydrogen bond. So it will selectively fluorinate this hydroxyl group, and this is used in synthesis of these many drug compounds. Okay, so you have variety of compounds in which you can have this fluorine here. Okay, so this is the advantage of late stage fluorination. Okay, you can do at the late, they have functional group tolerance, so you can do that fluorination without affecting other sites in your molecule. Okay, so deoxyfluorination using this pyridine based compound. Okay, now nitrogen of this pyridine heterocycle, what will it will do? It will have electron withdrawing inductive effect kind of thing, and that compound, this pifluor, you can use again for the displacement of OH with fluorine, and it is shown here that it can be displace sterically less hindered OH group. Okay, so you can have here means initially it was there a OH group which is secondary OH group, and you have tertiary OH group, but it only displays secondary OH group. You can also displace OH by keeping intact carbonyl group. Okay, so this is again another very good kind of reagent which you can use in your synthesis. Deoxyfluorination using CP fluor. So right now, till now, whatever reagents you have seen it has either nitrogen fluorine bond or it has sulfur fluorine bond. Now this is a cyclopropene which has this 2 fluorine atoms here. So this is the first all carbon kind of reagent which is used for fluorination. So this also displays OH and you can get fluorine here. So again this kind of reaction is observed with inversion of configuration. Fluorination of several steroid derivatives in which complete retention was observed. Okay, so even though it gives retention, if your moiety, if you are working with steroids, it will give you retention in configuration. This is due to homoallylic participation. Okay, so this you have to remember. Again, that CP fluor, cyclopropene based fluorinating reagent, it is used for the fluorination, and here it is displacing this primary OH group with this fluorine compound. Okay, in some cases unusual selectivity was also observed, means secondary OH group will be displaced instead of primary. Okay, so it is not hard and fast that always it will displace primary. It vary substrate to substrate and what the neighboring atmosphere in that molecule. If we see the reactivity trend, then electron-rich benzylic, that will displace more compared to secondary, then electron-deficient benzylic, primary, and electron-deficient secondary OH group. Okay, so this is the trend. So you have to see that in your compound what kind of OH group is there and which OH you want to displace. Okay, now you know that dust will displace this carbonyl with gem difluoro compound. Okay, you will get geminal fluoride here by dust. But if you are using this carbonyl compound and if you are using this tosyl hydrazine, it will form hydrazone and you will get here only one fluorine atom. So it will be addition of you can say hydrofluorination of carbonyl compounds. Okay, instead of 2 fluorine, you are getting hydrogen and fluorine at that place by first converting this ketone into hydrazone. Okay, so again means no need to, if you don't want to have 2 fluorine atoms here, don't use dust. You have to follow this sequence, then you can get only 1 fluorine atom there. Now for this kind of reaction where you want to fluorinate alpha position of aldehyde, you have to use electrophilic reagent, because all of you know that these protons are acidic, it will form that carbanion here and then you can use electrophilic reagent, you will have this fluorine here. Okay, but this is a little bit difficult because there is a competition of homoaldol reaction. Okay, but this you can do by selective fluor and you can get 73% of yield. But here there is, we are not talking about stereochemistry. If you want that enantiomeric compound, then you have to use some catalyst, and with that catalyst you can get, so with S-proline only, here also S-proline is used. Here with S-proline, if you see enantio selectivity is only 29% enantiomeric excess. Okay, again this is by using this reagent select fluor. Okay. Now again asymmetric alpha fluorination of aldehyde, you can do that by using this NFCI, N-fluorobenzene sulfonamide reagents. Okay, again these are electrophilic reagents, so you will have this in all kind of thing and then you can introduce this fluorine. Okay, so if you use this kind of a catalyst, you will get 96% yield and 99% enantiomeric excess was reported. Okay, so you can do fluorination in an asymmetric way also. Okay, so like sir has discussed that it is when you are having fluorine in drug molecule, you have to be very careful about stereochemistry. So asymmetric synthesis of this fluorination is very important, so that you can do by this reaction. Okay, so similar you can do for this compound also. Again you have to use NFSI reagent and you will get 85% yield and 98% of enantiomeric excess. Asymmetric fluorination of ketone via enamine formation using cinchonalcolide. Okay, so formation of this alpha fluorine compound, alpha to ketone carbonate, it is little bit difficult as compared to aldehyde, but that can also be done by using this kind of alkaloid. Again it will form that kind of hydrazone and then it will allow that fluorine only from one specific way, and that's why you can getting only one fluorine with that particular stereochemistry. Okay, and this is used for the synthesis of these compounds. I think this AC is not on. Okay, so asymmetric oxidation fluorination of aldehydes. So again we are seeing asymmetric oxidative fluorination. So here what we are seeing, aldehyde group, it is also getting converted into carboxylic acid and further it will form ester, and you are also getting fluorination at alpha position of this carbonyl compound. Okay, this can be done by using again NFSI, this kind of reagent, and you have to use catalyst like this. Okay, so whenever you know that some chiral auxiliary you have to use whenever you want to do asymmetric fluorination. So that kind of catalyst you have to use here. Sun's asymmetric oxidative fluorination of aldehyde. Okay, so again here means NFSI, it is introducing fluorine at alpha position, it is also acting as oxidizing reagent, so that's why aldehyde is getting converted into corresponding methyl ester. Okay, so this is reaction you can do with 1.1 equivalent of methanol. Okay, so you will get this. Again obviously you have to use this kind of a catalyst. Zakarian stereoselective alpha fluorination of N-acyl oxazolidine. Okay, so this is N-acyl oxazolidinone. For this compound, if you want to do fluorination at alpha position of this carbonyl, you can do with some reactivity of metal enolates. Okay, so you have to form that enolate, and that metal enolate further it will react with NFSI, which is electrophilic reagent, and you can have this fluorine here. Okay, and if you use some catalyst like this, you can get diastereomeric selectivity 93:7%. Okay, so you have to remember these things. Macmillan, now here he has used visible light mediated decarboxylative fluorination. Okay, so catalyst used was this, and instead of this carboxylic acid group, you have now fluorine here. Okay, and this can be done in presence of visible light. So you can have this 34-watt blue LED as that UV source, and you can do this reaction. And so many other substrates, they have seen reaction on this substrate where this carboxylic acid group was displaced with fluorine. Okay, so you have to again keep these things in mind. Silver catalyzed decarboxylative fluorination, again you can do this decarboxylative fluorination by using silver catalyst. Okay, first we have seen this iridium catalyst. Now you can use this silver nitrate and selectofluor, which is again a fluorinating reagent, and you can have fluorine instead of this carboxylic acid group. Now you can do aminofluorination, means if you have alkene, you can do addition reaction kind of thing, and you can have this amino group here and fluorine group here. Again, if you use palladium catalyst, you will get this kind of compound. So regiosymmetry will be different. If you use copper bromide, it will have compound like this. Okay, so I'm not going into detailed mechanism. I will share that PDF with you from where I have taken these examples. You can go through that and you can find out. But what I want to tell you that there are many reagents which will give you your desired compound. Wherever you want to introduce fluorine, you can do that. So advanced organic chemistry has become now. Catalytic difluorination approach. So now here you have seen that there was an alkene and you have only one fluorine atom. At this place you have amine group. Okay, now you can have both the position, both the carbon, you can have fluorine. Okay, this can be done again by selectofluor, and you have to use catalyst like this. Okay, so Jacobson and co-worker have developed an enantio and stereoselective difluorination of cinamide derivatives. Okay, so you can use such kind of reagent for this reaction. You can have cyclization reaction, either endocyclization reaction or exocyclization reaction. If you have endocyclization reaction, for that this particular compound you can have 6-member ring and you can have fluorine here. Okay, so or if you have exocyclic, then you can get 5-member ring and you have this fluorine here. Okay, so again you have to use your reagent, and you have to use your solvent system very carefully so that to get desired product. Aromatic CH fluorination. Now this can be done by electrophilic reagents. So you have some directing group here. You can convert this. You can have fluorine at this CH position instead of hydrogen. You can have fluorine. For that, first you have to treat it with tributyl magnesiation of aromatic CH. So this is called as a directed orthomagnesiation of aromatic CH bond followed by electrophilic attack of NFSI. Okay, so this you can do aromatic CH. Okay, for this again I am telling you that there are so many transition metal catalyst compounds are there which can do this reaction, but Ravi sir will talk about that. Okay, silver mediated chichibabin CH fluorination of pyridine and diazines. Okay, so we know that chichibabin reaction we get alpha amine compound at this position. So using same mechanism you can introduce fluorine by using silver fluoride and acetonitrile as a solvent at room temperature. Okay, so if you have this pyridine kind of thing, you can get fluorine at this alpha position. Transition metal catalyzed benzylic CH fluorination. Okay, again I am not talking about sp2 fluorination, I am talking about benzylic, matlab PHCH2. Okay, so this is a fluorination at this position, and you have so many molecules where you have this benzylic carbon where fluorine was introduced. Okay, so this can be also done by using transition metal catalyst. Okay, so you can use such kind of reagent to get benzylic fluorination, fluorination at benzylic CH. Palladium catalyze allylic CH fluorination. Okay, so if you have allylic CH, that can also be displaced and you can have fluorine there. Okay, and people have used manganese silane, this kind of a catalyst, to do this work. Okay, so doing this reaction also you can get fluorine at this benzylic position. Fluorination of unactivated aliphatic CH bond. So if your CH is not activated, if it is not at alpha position of carbonyl, it is not acidic. If it is not at benzylic position, then what to do? Okay. So for that kind of reaction also you can do fluorination reaction, and here there is an example where this hydrogen was displaced and you have this fluorine reagent using again selective fluor. Okay, so this palladium catalyzed aliphatic CH fluorination can be done for this compound. So here you can see that this beta hydrogen, okay, this is a carbonyl compound, this is alpha position and this is a beta position. So hydrogen at beta position is displaced by fluorine. Okay, so it is not activated CH, but still you can have fluorine at that beta position. Okay. So distereoselective beta fluorination of protected amino derivatives, that can also be achieved using this palladium acetate catalyst, and you can have this fluorine here instead of CH. Okay, so such reactions are also there. You can introduce fluorine at gamma carbon also. So you have this alpha, beta, gamma carbon from carbonyl, and that gamma position also fluorine has introduced. So you have fluorination at alpha position, beta position, gamma position. Okay, so in short, you have variety of reagent. You have to find out that what is your substrate, and you want to displace what, whether it is a hydrogen, whether it is OH, whether it is a halide, or whether you have double bond that you want to convert. So number of reagents are there. You can do that. You can use this reagents. Okay. So thank you very much for your kind questions.
Overall, you could see that there is a huge diversity of the reagents, substrates, but the synthetic chemists have advanced, as of now. You mentioned that so much that there are many different reagents are available. So this was very interesting review, where very diverse substrates. She has covered few examples. Diverse substrates are mentioned. So based on the kind of substrate you are working on, you will be able to plan appropriate solution for those.
And you discuss about DAS, that 7-membered was protected with walk, right? And one more point was there, pyrrolidine oil, that was also protected with walk. But in case of 7-membered, you told about the walk, effect of walk, how it is going to do in complete inversion from stereo center of hydroxy.
Yeah, I mentioned it is neighboring group participation.
Right.
In
So,
that?
but you showed one more example where the pyrrolidine was protected with walk.
Uh-huh.
Where the inversion was not, it was not there. So
Which slide can you please?
slide number was not there.
Yeah, slide number is not there, but
It had a double bond in the ring, so the conformational constraints you mentioned.
In case of gas.
here?
No, go back. This one.
One more example like that, you covered about pyrrolidine. Pyrrolidine is protected with gas. Sorry, walk. This one. So here it is. And
It was in that model.
You got
That previous
confused.
slide which I mentioned, in both the substrate there is a walk, but in one there is a double bond. Because of that double bond,
That he got.
conformational constraints will not allow the AGP, the Golden participation, and that's why the reaction was not very workable. If you can explain that on the slide. we have prints for today, right? So try to see. I don't know if there's a time to get the print because from the office it may not be possible to print out. So the second day thing and the third day. So my request is to get that printed. Okay? Is it possible, right? We'll be able to print that those slides so that it will be easy for you to follow